Hello, everyone. It's Jimmy Nguyen, founding president of Bitcoin Association, and it is my pleasure to welcome you to the 2021 Bitcoin SV DevCon, the developer conference that we host to help educate developers across the world of all experience levels about the power of building on the BSV blockchain. Bitcoin SV is Bitcoin, a blockchain and digital currency for everyone, everywhere, and everything. There's immense power in the protocol, and you'll learn all about that today. I have with me our host for the developer conference, Steve Shatters, who will introduce in a little bit. But Steve, say hi.
Hi, everyone.
Steve, for all of you who out there who know him, is the Chief Technology Officer at nChain and is also the chair of the Technical Standards Committee for BSV at the Bitcoin Association. And he's also the technical director of the Bitcoin SV infrastructure team that manages the node software and many of the free tools that are provided to help all of you out in the ecosystem build with BSV infrastructure. So he has a lot of hats and is the ideal person to navigate you through this developer conference. We
lost the signal for Jimmy. Might be a bit of a Zoom glitch. So it looks like he might have rejoined us.
Yes, I'm back. Sorry about that. Zoom glitch. I was just saying we're having a promotion throughout the developer conference during the breaks, where we are going to be giving away airdrops where you can win $1 worth of BSV, $1 worth of BSV through a QR code that will appear on screen. You can only get one per person. That will be available to get to your Handcash wallet. If you don't have a Handcash wallet, it will take you to the place to get one. In addition, CoinGeek Zurich is coming up, one of our two big CoinGeek events every year that we partner with CoinGeek's media and event team to run. It's the leading business conference for Bitcoin SV. It's based out of Zurich this time, June 8th, 9th, and 10th. It is free to register. It'll be appearing virtually across the world and another broadcast style event with some people in person in Zurich. Go to coingeekconference.com in order to register. Please join us for what will be a powerful event as we learn how to ignite the power of data. Now, Steve, we'll turn it over to you to give us an overview of what will be happening over the next 2 days here at DevCon.
Thanks, Jimmy, and welcome to the application developers in the room. You guys are the first layer consumers of the network services that are provided by the Bitcoin miners. And as application developers, your fundamental task is to build transactions and package them up in new, useful, interesting, and creative ways so that you can best deliver value to the users of your services. And that's what the next 2 days is primarily going to be about. We're going to be showcasing a whole lot of different tools that can help you in achieving that task. The tooling ecosystem in Bitcoin SV is always growing. There's always something that's still missing that would just make life a little bit easier if it was there, but perhaps that's even a gap that some of you can fill. But there already is a lot there, and it's growing all of the time. So just a quick summary of how we're going to do things over the next couple of days. There are going to be a number of presentations on each day, and I'll get to what some of the content of those presentations is going to be shortly, followed by a live Q&A session with the presenter. So you'll see there's a question and answer box on the screen that you're probably watching on. You don't need to wait until the end of the presentation. You can type in your questions at any time, and they'll all be queued up so that I'll be able to read them out to the presenter at the end of that presentation. If there are questions that we don't have time for that go unanswered, we'll be giving the questions offline to the presenters so that they can give you a written response, and we'll be publishing those for you. So don't worry, we'll get to all of the questions one way or another. So a quick summary of what we're going to talk about. Well, we've got a lot of content over the next couple of days. On the wallet side, we're going to be hearing from Handcash, Wallet, and Electrum SV, all of whom have SDKs to show off. They all some of them solve similar problems, but some of them are quite different. Electrum SV, for example, is a development environment that is useful even if you're not using Electrum itself. There's a lot of tooling around. We'll be hearing from the Bitcoin SV Academy education team. They'll be telling you a bit about what they're doing and how you can make use of the Academy to upskill yourself. We'll have some people from nChain who'll be showing some of the Bitcoin infrastructure tools, as well as some interesting different ways that you can build transactions. And then we'll be hearing from Aaron Russell at Kronos Labs, and I'm actually not sure which tool he's going to be showing. They have been very prolific in building a lot of tools. The first one I noticed was called TX Forge, which is a library to basically help you construct transactions, which was a one of a kind, I think, at the time when it came out. But who knows what new things Aaron has been working on. And then we might get to some of the more wacky and esoteric stuff. Xiaowei from Scrypt is going to be telling us about the ins and outs of push TX and the fantastically powerful ways that that technique can be used. And we're going to hear from Fix, also known as Chronoverse, on under the hood with crypto fights, but also some interesting tooling that will be available to you to make use of. And of course, at the end of today, we're going to have a fireside chat with none other than Dr. Craig Wright. I'll be hosting that. It'll be a virtual fire this time because we're in different cities, but I'll be delving into some of the reasons why certain technical decisions were made in Bitcoin. So that should be an interesting conversation. So we are going to kick off at 20 past the hour with our first presentation. There might be a short break in between some of the presentations, by the way, just so that we stay on schedule. But while we're waiting, I might just take a moment to talk a little bit about the Bitcoin SV 1.08 beta release that happened a couple of days ago, along with a companion release, MAPI 1.3. And there's a few sort of notable features. I will be actually talking about some of those in my own presentation, along with Matej Trampush, the engineering director of nChain, which I believe that is happening tomorrow morning. But just briefly, some of the features, the ancestor limit that has probably been the top of the agenda for the last 2 years. We made first steps in improving that in 1.07 back in January. There have been some challenges in getting that rolled out, and we'll take a moment to kind of explain some of the reasoning behind that. First things first is that the accounting mechanism that's used to work out how long a chain actually is can work in a number of different ways. And if you're trying to attack simple chains of transactions where you just have one following the other, then the optimal and easiest to implement algorithm is different to if you're trying to address complex graphs of transactions. So in the 107 release, we elected for the simple option because we knew that the majority of use cases for it did use that simple mechanism, rather than making everybody wait another 5 months for us to implement the more complex version. Of course, the other complication is adoption. When you raise the limit to 1,000, that's people, I think, tend to assume that means 1,000 every block. That will work if every single miner has adopted that. But if, for example, only 20% of the hash rate have actually adopted the upgrade, that means that only one in every 5 blocks is able to take the full limit. So that actually reduces the effective rate. But in this version of it, Bitcoin SV, we've not only implemented the accounting mechanism that can handle the complex graphs, we've also increased the limit to 10,000. So that will help substantially. We actually think that we probably could push it a lot higher, but just out of an abundance of caution, we're doing a little bit more testing first. But I can tell you that it's absolutely on the roadmap, possibly even in the next release, to strip the limit out altogether. A couple of other features, dust return transactions, which I'll tell you about in a lot more detail when I present with Mate. And an update to the way that double spend notifications work, which Mate will be telling you about. I'm particularly excited about this one because I believe that this is the last missing piece of the puzzle to make Bitcoin SV 100% zero conf safe. So more detail on that from Mate. I won't steal his thunder. So we're just going to take a short break now, just for 5 minutes, and at 20 past the hour, we will be back with a presentation from the Bitcoin SV Academy. Thank you. Welcome back. We have our first set of presenters ready for you, and it's the Bitcoin SV Academy. They're here today to give you an overview of the new developer course and focus on BSV library. I'd like to welcome Brendan Lee, Conor Murray, Evan Freeman, and Kapil Jain, the Bitcoin SV Academy team.
Hello, and a warm welcome to all of you from the Bitcoin Association education team. My name is Evan Freeman, a curriculum specialist at the Bitcoin Association, and I'm honored to be presenting to all of you today. I'm located in the tropical islands of Hawaii, and as you may or may not be able to tell, I am an Ewok for today. Although these days I am a big fan of Chewbacca. For one, I look a bit like him. I'm tall and hairy. Sometimes I make strange noises. But like Chewie, I enjoy archery and eating, as well as just going a bit wild out in nature. Enough about me. We set forth 1 year ago to build the greatest Bitcoin educational resource in the galaxy, if not the greater universe. We did so because we knew just how dangerous ignorance can be to a growing ecosystem, and the potential for that ignorance to be manipulated towards the dark side. Without knowledge or the desire to find the truth, we become vulnerable to false expectations, the desire for power over others, unrestrained greed, and the self-deceptions it harbors. The path that a Jedi follows is a path that brings forth knowledge and the acceptance of reality. Once we accept that in reality, we are all more alike than different, and that for humanity to truly achieve its potential, we must work to create an environment that rewards positivity, that rewards hard work, and rewards the commitment to truth and knowledge. We begin to become better aligned with the positive nature of the Force. The Bitcoin Association, under the direction and guidance of Master Jedi Jimmy Nguyen and Raylene Wilson, has committed great effort to build exceptional courses covering many facets of Bitcoin, 2 of which are available right now. The BSV Academy's Introduction to Bitcoin Theory course is designed by the legendary Jedi Brendan Lee Kenobi. It focuses on understanding the Bitcoin white paper, as well as the BSV Academy's Introduction to Bitcoin Development course, designed by the swashbuckling space adventurer smuggler Kapil Solo, with more coming soon, very soon. Ultimately, the BSV Academy focuses on the building blocks necessary for students to achieve highly competent professional understanding of Bitcoin for use in the corporate or startup world. We have seen way too many Wookiee mistakes to know just how important it is for businesses to be able to hire certifiably knowledgeable staff. So if you're interested in these courses and you would like to hear more, stay tuned as we will have our heroes discussing these courses in greater detail in just a few moments. Additionally, we will hear from a new hope, a recent, youthful, and very promising addition to our team, Connor Skywalker, with a special announcement. The Force is strong with young Connor and with all of you watching, and I hope we can assist all of you on your journey, no matter what your knowledge level is. Thank you.
Good evening. My name is Brendan Lee, and I'm the Training and Development Manager for the Bitcoin Association. I am from Brisbane, Australia, a location renowned for its river having the highest concentration of bull sharks of any body of water in the world. Only in Australia, folks. It's also where I met Steve Shatters and where Craig Wright was born. So I reckon there must be something in the water. The thing that really drew me to Bitcoin, I think, was was its potential to be a means for everybody in the world to have open and equal access to financial services, and for its ability to take what traditionally costs many dollars and is inaccessible to, in some parts of the world, a big majority of the people, and make it accessible. And it's that kind of transformative change that I could see so clearly and wanted to be a part of, and knew that I could do something to accelerate this, and that if I could, that would help a lot of people. The thing that Bitcoin SV represents to me is the implementation that has the best chance of delivering that vision. So having billions of people connected, servicing billions of transactions every day for all kinds of things. And that's traditional goods and services, as well as new types of digital services that give us much more open and ready access to the content that we want, and really allows us to choose the means by which that is delivered to us and how we consume it. And I really love working in this space. I think it's the most exciting industry in the world at the moment. So the Bitcoin SV Academy really came about after a few conversations between myself and the program manager, Raylene, and really just about what we wanted to build in terms of a resource. And once we looked at it, it really came about that what we needed was a system that we would have to deliver over multiple years, and with multiple streams and multiple levels of courses. And so what you see now, which is the 3 streams that we've set up, theory, infrastructure, and development, form the first 3 legs of that strategy. And so within each of those streams, we will very shortly have the introductory courses available for free, and those courses are each designed to take about 10 hours each, and really to transfer the important knowledge that you need to leverage the superpowers of Bitcoin in your projects. So Introduction to Bitcoin Theory is a line-by-line breakdown of the Bitcoin white paper. And the intent really is to explain the white paper, to break the white paper down in a very granular manner. So the Bitcoin white paper is an exceptionally dense document. You can take one line of the white paper and write 5 pages about what it means, or even more. In a lot of cases, one of the most difficult parts was to actually condense the information that we needed to get the core ideas across as clearly as possible. And it's testament to the creator's economy of words. That entire system is squeezed into an 8-page document, including 2 pages basically of maths and calculations. The second course I've worked on at the Bitcoin SV Academy is Introduction to Bitcoin Infrastructure. Introduction to Bitcoin Infrastructure really is a deep dive into what it is to operate a node and what a node must do on the Bitcoin network. And so the first part of that course is a deep dive into section 5, or is a very close look at section 5 of the Bitcoin white paper, and in particular looking at the 6 instructions at the beginning of the chapter that really are steps for how to be a node on the network. And in this course we refer to these as instructions because in fact what they really are is a set of instructions that you need to follow in order to be the best, most competitive node on the network. And we can show this in each case by looking at the behavior that the block reward and proof of work creates, and to demonstrate that really it's a highly competitive process where at the center of the network you have this total open honesty between the competitors in the system. And it's that total and open honesty that really drew me to Bitcoin, is one of the most interesting things about the system. It's that at the center of our financial service globally is a system predicated on being the most open and honest participant in the process and making that the most profitable path to take. To me, that is one of the core magic powers of Bitcoin, because it's what incentivizes the whole thing to kind of spontaneously assemble and really become this future machine. And it's really hard to even grasp what these computers are going to look like in future, but they're going to be vastly different to most of what we have today. And it's going to be really interesting to see the evolution of that. So this course really is a close look at the life of a node operator and the functions that a node performs. The ways in which the design of the system incentivize those node operators to compete with each other, to be the best, and to actually build the network. And I think this is one of the core things that's very misunderstood about the incentive structure of Bitcoin, is that the whole thing causes this public infrastructure that we will all grow to depend on to spontaneously assemble into this highly robust, highly high speed, low cost network without any centralized power. And that's the magic. And it only works if you go big, if you go huge. And so this course really is a first look at that, a look at the honesty at the core of the system, a look at the incentives that take that honesty and turn it into a competitive driver for technology development and infrastructure, and then to look at how that competition is arranged through the application of fees and how transactions are handled, all of these different things. And look, I really think that you're going to get a lot out of it if you are building services that use Bitcoin as a layer. And especially you're going to get a lot out of it if you want to work in mining. And so please do check it out. How has creating this course helped me to better understand Bitcoin in general? I think collectively the courses and the wiki have mostly helped me to better understand the terminology and how to describe the system, and a lot of the nitty-gritty, so the little details, the little things that you didn't know about that actually turn out to be real superpowers of Bitcoin. And it's a lot of the things that I work on involve those superpowers, and knowing them is really what is going to give you a leg up in this game. And these courses are here to give you those same nuggets, that same knowledge, with that knowledge that you'll be able to figure out how to solve those problems and how to build those next generation platforms and services and really bring the future. I would definitely say that Introduction to Bitcoin Theory is suitable for just about anyone. If you are just interested in the system, I would still recommend doing the course. It doesn't cost anything. It's quite challenging. So please do try and stick with it. I think that there is a payoff. I really, really hope a lot of you get a lot out of it. It's really going to give you a lot more context around how your transactions are handled by nodes and the things that you need to understand when you're building your service and building the parts of that service that put your transactions together, because it is how those transactions are assembled that will determine the speed with which they are accepted by the network. One of the things that I really hope will come out of this course is that employers will be able to use the certificates that we are giving out as a real barometer of somebody's take on Bitcoin. And so to be able to see that certificate there and know that this person has studied the core material and understands that everything about the system depends on that 10,000 foot view of this being a massively scaled global network that billions of people a day are using. And everything that happens on this system must be designed with that in mind. And these courses will really start to help you to understand more of what that means. And so for employers, they're going to want people who have those to really make that selection process much quicker.
Hi everyone, I am Kapil Jain and I'm working with Bitcoin Association as a curriculum contributor. I'm sure you all would have seen Star Wars and are probably aware of the philosophy behind it. The mythology of Star Wars has been inspired heavily by the works of someone named Joseph Campbell. Joseph Campbell was an American scholar who did extensive research in mythology, religion, and journey a human takes in their quest to find the truth. Discovery for Bitcoin to me was in a way also my journey to find the truth. After spending more than a decade in the conventional solutions for banking and payments, last year I made a conscious pivot in my career and now I work full-time with Bitcoin. Personally, to me, Bitcoin is not only an innovation, it is also the right way of doing things. It is simple and yet it resolves the structural complexity and constraints in the existing solutions. Bitcoin came into existence more than a decade ago, which introduced the world to a concept of peer-to-peer electronic cash system. This made people think that Bitcoin is money, which it is. Bitcoin really is a way to create truth through data ledgers. It enables to record transactions in open, public, and transparent manner, which is immutable and distributed. Because of that power of Bitcoin blockchain, it can be used for many other things than just payment transactions. It can be used to power a whole new world of data transactions for smart contracts, tokens, Internet of Things, healthcare, and finance. Today, Bitcoin SV, which represents the only implementation of original Bitcoin protocol, exists as one single truth among thousands of blockchains with an ocean of misinformation around this technology. To be able to get to the truth, anyone new has to walk through a plethora of misrepresented facts, make-believe ideas, and a luring greed of getting rich. And it's only when you cross these hurdles you find the treasure. And the treasure is the truth of technological innovation that Bitcoin really is. It is no less than the journey that we see in Star Wars that many heroes take. It's kind of a similar journey a person needs to take. And the purpose of BSV Academy is to shorten that journey for you and give you access to truth directly. I have been involved in the development of the first course in the Bitcoin development stream. It is a stream because we plan to release a whole set of developer-focused courses in future. We've started with the first course, which is called Introduction to Bitcoin Development. This course is an attempt to provide a comprehensive view to a developer without the expectation of any prior knowledge on blockchain or Bitcoin. It is quite difficult to cover Bitcoin protocol and all that is possible to be developed with it in one course without making it almost like a semester in a degree program. So this course will give you the necessary required concepts and details that you need to get started with development using Bitcoin blockchain. Few, but not all sections in this course do require you to have basic JavaScript knowledge. However, the concept covered and explained are not coupled to any programming language in particular. This stream and course is important as it caters to most important stakeholders in any software development paradigm, and that is you, the developers. The course covers the breadth of concepts involved in application development using Bitcoin. And this course is kind of a natural progression to the first course that we offer under Bitcoin SV Academy, which is called Introduction to Bitcoin Theory. This course will expose you to few of the tools, protocols, and libraries created by many brilliant developers and companies in the ecosystem. I, in fact, thoroughly enjoyed writing about them and actually learned a lot while writing about them as well. And I believe that you will too. With that, I want to say that this is only the start of journey of enlightenment and learning with Bitcoin SV Academy, and there is much more to come in future. I am excited to welcome you all, and may the force be with you.
Hello and welcome. My name is Connor Murray, and I'm a course content creator here with the Bitcoin Association, working on the Bitcoin SV Academy. I'd like to formally welcome you away from the dark side and into the light as you work to develop applications built on the original Bitcoin protocol. This Bitcoin protocol is fulfilled by the Bitcoin SV blockchain, and it is the first time we've had the original Bitcoin protocol restored under one global scalable blockchain. Satoshi Nakamoto was passionate about introducing light and transparency to the world, and we at the Bitcoin SV Academy are passionate about educating the world on Satoshi Nakamoto's vision for Bitcoin. You see, Bitcoin SV is a lot like the Jedi. It is surrounded by a dark world of cryptocurrency. This cryptocurrency ecosystem has made many promises but failed to deliver on almost all of them. Bitcoin SV can do everything that every other cryptocurrency claims it can do. It's really important as you build applications to understand that Bitcoin, as it was designed by Satoshi Nakamoto, was built to enable microtransactions and also built in with a native scripting language that allows all sorts of complex applications to emerge. Bitcoin SV has a tall task ahead of itself, but because it's the only blockchain that can do everything, it will win. I was first introduced to Bitcoin in 2013, and I followed it for a number of years until finally it decided to scale on-chain and fulfill its vision for microtransactions. I'm here to announce the introduction of the Bitcoin Essential stream on the Bitcoin SV Academy. Up until now, most coursework was longer, and between the Bitcoin theory course and the Bitcoin development course, it took a long time of in-depth study to complete each course. While this is very valuable for people looking for advanced knowledge, it was important for us to have shorter coursework to cover specific topics, and I'm here to happily introduce the first course titled Bitcoin Basics. I designed the Bitcoin Basics course to introduce Bitcoin to any audience member, experienced or beginner. The Bitcoin Basics course is the first time that we introduced a fundamental understanding of Bitcoin rooted in the knowledge that Bitcoin is what Bitcoin SV fulfills. And what I mean by that is that most other Bitcoin education courses do not talk about Bitcoin's creation as a microtransaction-based digital cash system. It does not mention Bitcoin's native scripting capabilities to do all sorts of complex computation. The Bitcoin Basics course is a short 2 to 3 hour introduction for anybody, beginner or experienced, to get a solid foundation of understanding on what Bitcoin is. It was important for us to develop this course because there are a lot of other Bitcoin introductory courses out there that charge money, and they go over so many false narratives about what Bitcoin is that it does not allow the student to get a grasp for why Bitcoin is important to begin with. While this course hasn't necessarily helped me understand Bitcoin in greater detail, it has forced me to distill what is important about Bitcoin into a short course. And I've learned that when talking to anybody that doesn't know anything about Bitcoin, it's important to do what Satoshi did, which was introduce why it was important to begin with. It wasn't important as an alternative to gold. It was important because the internet needed a microtransactional based digital cash system. And that's what Bitcoin fulfills. This course will hopefully allow an introductory certification to be granted to people, whether you're an employer looking to educate your employees on what Bitcoin is, or if you're an employer seeking out qualified individuals not only the Bitcoin Basics course, but the whole Bitcoin SV Academy certification will be crucial to your employees' understanding. I'm really thankful that you're here, and I hope that you introduce yourself to the Bitcoin SV Academy. Take all of their coursework because it is the highest quality education you will find about Bitcoin across the internet. Thank you so much for working on the Bitcoin SV blockchain and introducing light into this dark world of cryptocurrency. Thank you.
Wow, that was absolutely fantastic. And I really hope that some of you may have found a course that is perhaps something that you are interested in. And if so, I urge you to go and pursue that course. I would like to give a great big thank you to all of these wonderful Jedis of our Bitcoin Association education team, as well as all of the other Jedis that are presenting at this great event. And of course, all of you watching and listening, thank you. We at the Bitcoin Association education team hope that all of you Jedis out there feel inspired to deepen your knowledge of Bitcoin and urge you to explore our academy and offer us your feedback. You know, a lot of you are all very knowledgeable, and so we can learn from you as well. Share your knowledge with us, take the course, and improve the ecosystem together. So please visit our academy at bitcoinsv.academy to learn more or to join any of our courses and deepen your knowledge of Bitcoin. Thank you, and may the force be with you.
Hello, my name is Princess Leia. Please join the Bitcoin Association Academy. May the force be with you.
Dub dub.
Bye.
Thank you, Bitcoin SV Academy team. Education is something that's been pretty dear to my heart since the first days of Bitcoin SV, and I'm really glad to see that we actually have a dedicated team focusing on this. We've got a few audience questions, but before we begin, I've got one of my own. I heard a rumor that your course content has actually been reviewed by Dr. Craig Wright himself. How did that make you feel when you heard he was about to do that?
A little trepidation, I guess, was the first thing. Is like, you know, the creator coming to have a look, but you know, the sky hasn't crashed in on my head yet, so it can't be too bad. And as far as I'm aware, the feedback has been pretty positive. So I'm just very glad that you know, he thought that we'd come so close, and yeah, it's great. I'm very happy actually that that's finished. You know?
You can't really set the bar much higher than writing about the Bitcoin white paper and then submitting what you've written to Craig for his review. So I think that's a big congratulations to the entire team for surviving that trial by fire. So our first audience question is from I'll Connect. It's an interesting question because it could be interpreted in two ways, and I would probably like to hear you answer both versions of the question. How does running a node contribute to Bitcoin SV? And where is the best place for someone to start looking for a further understanding of Bitcoin SV? I'm going to guess you're going to say the Academy. But that first part of the question, how does running a node contribute to Bitcoin SV? I'm not sure if they're asking about running the Bitcoin SV software, or if they're asking about running a node according to the strict definition of Section 5 of the white paper. So perhaps you could answer for both cases.
Yes, sure. Well, I guess there's running a node. So I might cover running a node as it's defined in the white paper, and maybe we can jump to Kapil, who can talk about what else you can do with the node client software. But running a node as a commercial enterprise is obviously very helpful to BSV. It's the act of collating transactions and actually building the blockchain that we all use to check what's happened. And it's really something that I think is enormously important to the network, and something that it's a commercial choice to make. It's not something that really anybody's expected to do out of altruism. So if you're asking, does running a node in some manner help to secure the network? Well, if you're running a node that actually has hash power and is building blocks, then yes. But if you're just running a node client software and it doesn't have any access to hash power, and it's not adding blocks to the blockchain, it's not really doing anything to secure the network. But you might have other needs for running that software, and that can be very useful. Kapil,
I would say it would be very beneficial for the person to go through the Bitcoin theory course, or even just the basics course, to learn more about what a node actually is, and cover section 6 of the white paper in a good amount of detail.
True.
Yeah,
I would also say,
sorry, Kapil.
I would also say there should be a purpose behind running a node. So what Brendan explained, that's the main purpose. But if someone wants to run a business for providing data archival service, so that could be another reason for someone to run a node. And there's actually one more thing which is not that talked about, and it's not really about full node, but it's just about block headers. So if you actually, I know that currently we don't have an SPV available in the ecosystem, and I hope to see it soon. But if you actually have block headers downloaded anywhere, that acts as a security mechanism for a very, very unlikely scenario of a attack where a reorg happens, and that will be invalidated by these block headers Merkle root that is stored in these headers. So there are various scenarios. It depends on the purpose why you want to run a node.
Okay.
And may I just add, also there's an additional benefit to businesses in running a node, particularly if they're dealing with immense amounts of small transactions or transactions of any size, really, in order to be able to better monitor the incoming transactions for themselves.
I would tend to refer to that as a blockchain listener or a blockchain subscriber. The word node has a very specific meaning, which means that it does create blocks. But in fact, I think I might have made the comment myself in some public presentations in the past that running a node actually does cost money, and as the network scales, it costs more and more. So you actually need a good reason to do that. And of course, the main reason to do that is to earn revenue from block rewards. But we'll certainly be hearing a lot more about SPV throughout this DevCon. So we'll elaborate on the alternatives. The next question, I might throw this one to you, Evan, is very specifically about the course. What is the target audience for the infrastructure and theory streams?
Well, yeah, generally we're looking for individuals who are wanting to expand their knowledge about Bitcoin. So that could be generally or specifically, whether they're wanting to build an application or provide a service that has never existed before. We're here to make that possible. But on the other side, we're also here to assist businesses in expanding the knowledge and expertise of their existing staff, as well as to grow the overall talent pool. So, there's a lot we can offer to a variety of different individuals and businesses and organizations, but ultimately it's all about finding what Bitcoin can deliver to the world and then educating people on that.
I think in terms of value add for business, I can definitely attest to that because I've actually asked for every staff member at Enchain to go through this course, and not all of them have been able to get through it yet. Some of them haven't even been able to start yet. It's an ongoing process, but my general experience is that immediately after doing that course, they basically find it easier to do their jobs better because of what they've learned. So. I don't want to make this sound like a sales pitch, but I've firsthand seen the benefits of it. So I think a question that probably pops back to Kapil, because you mentioned this earlier, Timo is asking, where can I download block headers other than the Bitcoin SV software itself?
Don't have a good answer to that, but maybe
you will have a good answer in a couple of months, though, right?
Exactly. I mean, that's something I can say that we should be having a very good answer in a couple of months, hopefully. But yeah, that's something that has been lacking overall till now. I know of some wallets in probably a couple of years ago who tried SPV, but they don't exist anymore. But hopefully we should be changing that soon.
Another, I guess, an administrative question about the course is: can I take as long as I want to complete the course, or are they timed?
Yes.
As far as I know, you can take as long as you like. There's no.
And at least I can say for the developer course, it's designed in a manner that you do take time to do it. There are many concepts explained, and once you read the concepts, you do some hands-on, so you get to know the concepts better in practice. So yes, it's on you, like how quickly you can do it.
Sure. Okay. And what sort of topics are going to be covered in the Essentials courses? Maybe Connor?
Yeah, well, so the first course is just a basics course, but the purpose of the Essentials course is to condense things into shorter form coursework. So if you take the development course or the theory course or the infrastructure course, all extremely thorough, going to take you, probably closer to 8 hours to complete everything. But we're trying to do the Essential stream to be more 2 to 3 hours in length. And so, as far as the basics course, it really shouldn't take someone more than 3 hours to complete from beginning to end. And what we can do is provide shorter coursework to condense need to know information, but it doesn't mean that the Essentials stream will be just basic coursework. So the next course that we have, I won't spoil what it is just yet before we get everything fully condensed in, but there's a lot of information that we can, maybe we could cover, for example, what a Bitcoin transaction is, and from beginning to end, what a locking script is, what an unlocking script is, right? We can cover that in a shorter form where it's just focused on Bitcoin transactions, and the Essential stream will hopefully just condense complex topics into shorter form coursework to help make you an expert on one specific thing.
Okay, thanks, Connor. We've still got a few questions left, but we're running a bit short on time. So I will submit the remainder of the questions to the Academy team, and we'll get written responses for them, and they will be published, I think, on the DevCon website itself. Keep your eye on Twitter. I'm sure that we'll get the links out to that. Just as a final point, Will Devine notes that What's on Chain actually does have a block header REST API endpoint, and I would have to double check this, but I wouldn't be surprised if MatterCloud probably does as well. So there are certainly ways that you can get hold of Bitcoin block headers at the moment. There may not be the solution that you want going forward long term, but more solutions will be becoming made available soon, I think. So thanks very much to the Bitcoin SV Academy team. And please do check out their site, bsvacademy.com. I'm pretty sure it's a .com. I'll get corrected pretty soon if it's not.
Bitcoin SV.academy.
Sorry, Bitcoin SV Academy. Okay. Yeah, I'll double check my URLs next time. We'll be back in a couple of moments with a look at .wallet SDK, and it's a lot more than just a wallet. So we'll look forward to finding out more. We'll see you shortly. Welcome back, everybody. Nguyen is one of the oldest of the old guard in Bitcoin SV. He was there before the 2018 hash war, even rallying miner support. And many of you will know him as the man who created mempool and continues to mine BSV under the mempool banner. Right up until today. But of course, Lynn's team is very busy with a lot of things outside of just the core mining business. Dot Wallet is something that they've been working on for a very long time. And in fact, they've come up with an entire SDK that covers far more than just core wallet functionality. He has a very keen interest in the token exploring the token space, as well as many other things. So I'd like to welcome Nguyen. He's going to be telling us a lot more about the Dot Wallet SDK.
Hello, everyone. This is Nguyen from Dot Wallet and mempool. I'm very excited to be invited to present the new features from Dot Wallet for developers on Bitcoin SV DevCon. The Dot Wallet for developers is a coinless blockchain information system that can help the users to use the Bitcoin ledger without touching the coin site. It is a developer infrastructure that includes technique and marketing. It is combined with both keychain management, which is provided by Dot Wallet, and Bitcoin SV blockchain access, which is provided by mempool. You can get the access to millions of users using the platform. The main feature is payment, login, API, batch token services, and more. I'm going to introduce two new features today, and we can start from the peer-to-peer. Peer-to-peer is written in the Bitcoin white paper, and it helps the better protection of privacy. Because the users are using peer-to-peer to exchange information directly, so that helps to minimize the resources that is required to exchange those transactions. Only through the peer-to-peer network, we can scale Bitcoin. Currently, we need a way to be connected to wallet services. Different wallet services need to communicate with each other, either by the peer-to-peer network, or they can connect to the mining network, and then they will filter every transaction on the network to find out which one is wallet concerned. That way cannot scale. We need to focus on the P2P part and using the peer-to-peer method to connect directly. But currently, trusted third parties are still needed, like those wallet services like Money Button, like Dot Wallet, and Handcash. Although we already deployed our peer-to-peer solution, but we still need an online server that take custodial of users' public key to help the user to send and receive transactions. The XPub which is code, and the HD wallet contains a lot of private information. Those private information are very important and should be kept private. But the user cannot easily switch to different service providers because of the name of the paymail is fixed. So the paymail and BIP270 are used to connect different services providers, not peers. The users are limited to a specific service provider, and the user's privacy is kept by the service providers. Paymail is based on email, which is not favorable in China and many other countries because the characters, the letters in Paymail is much harder for non-English speaking people like me to pronounce correctly. So we present a different new technique to help to solve the problem. The first one is WinTalker. It's a trustless message forwarding services. And .id, which is a decentralized identity protocol. Let's take a look at the WinTalker. Basically, it consists three parties. One is the sender and receiver. And two is the service provider. And there should be another service provider to forward information between them. So we can see this topology. So we can see this graph when the sender, which holds the public key A, need to send their message to public key B. Then public key A, the sender, will query the service provider, which might be a miner using their miner ID, or they may be service providers. They have their non-public keys. And they all holds a routing table, which represents every non-public key on the WinTalker network. And the gateway, which points to how we can get to connect it to the receiver. And the local socket is how they can be connected through the local network. And the matrix means the fee required to be connected. So when the public key A need to find public key B, he will query the miner to find out how to connect to public key B. Then the miner will find out that they can be connected through like miner ID 3, then miner ID 4. Then the miner will forward the message from public key A to public key B. And because both the public keys are well known, so they will encrypt their message peer-to-peer. We provide a virtual connection between two peers to allow one public key to send messages to another. let's take a look. So we have Alice and Bob. Alice first, they were founding a payment channel with miner A. And miner A will record this payment relationship in a routing table locally. Then the miner A will synchronize the routing table with miner N and exchange information in between them. The receiver, Bob, will do the same thing with miner N. When the Alice want to send message to Bob, they will send the request to be connected to Bob to miner A. And miner A will inform miner N through the query of the routing table, because even miner A does not know Bob. There is no direct connection between them, but miner A can still ask miner N because miner A knows that they have direct connection. So the miner A will forward the message to miner N and pay several Satoshi fees. Then the miner N will inform Bob, send the message directly to Bob. Then Alice and Bob can establish a virtual connection, which is peer-to-peer, and send messages with each other. The best part here is the routing table. How we could synchronize the routing table. Because when Alice and the miner form a payment channel, they have a specific template to organize the payment channel. And the funding transaction has been included in the mempool or the blocks, so that every miner can update the routing table through the receiving of the new blocks. They can find a pattern and to find out, okay, the miner A has several new users, which is Alice and Charlie and so on. They can do that permissionlessly, just using the new blocks. Or they can use a gossip network in between different service providers, so that the new channel will be broadcast. The new payment relationship will be broadcasted using the gossip network, so that the miner A and the miner B will be in sync. And because the relationship is funded by tokens or Bitcoin SV, so that it cannot be cheated. Every user on the network will have a very high confidence that those identities are using different services. That is the routing table. And the user can even connect to different service providers using different fee structure. But the routing table can still be synchronized between different service providers. How to establish the connection? Alice will send a request to miner A via direct connection, because the user always need a direct connection to a miner, right? And the miner, when the miner A receives the request, they can send a request through established payment channels between different miners. So miner A and miner B are also connected and use the payment channel to exchange information and collect fees. Then the miner B will find out, yes, they can deliver the message to the receiver, to Bob. Then the information are sent to Bob using direct connection between miner B and Bob. So the request is responded by Bob via the virtual connection. The connection is established. When Alice wants to send the message to Bob, they will ask the miner to query the routing table to find out whether they can connect to Bob directly or through which party they can be connected. So in this situation, there's no direct connection between miner A and Bob. So miner A will forward the message to miner N. Okay. So have a conclusion that every user here is bounded to non-public keys. They can have different public keys to use the services. And the service provider could catch and index the payment channels that other service providers have established in order to form a routing table. It provides resilience and without any trusted third parties. Routes could still be queried permissionless because you can always get new blocks and to find specific transaction template. Those message forwarding services like email, you can always set up your own email server. It can be self-served. The best part here is that we can reuse the bandwidth and the infrastructures provided by miners. Miners are incentivized to be connect to each other, and they can pay the usage of the infrastructure by payment channels. So even different service providers will not provide free services to forward those information. They can still collect enough fees. Remember, we have matrix column here in the routing table. The lowest fee will win. So you could not charge for a premium and hopes that someone will deliver message through your services. You only charge for a reasonable price, and so that the routing server will try to use your forwarding service. And WinTalker can be integrated into Paymail. And it's like email services. It's a federated network and hub-spoke topology. The fees could be collected using payment channels, which could even be tokens without using BSV. It protects privacy because every communication happens peer-to-peer and is end-to-end encrypted. The forwarder could be trustless. They are incentivized to offer better service. Okay, that's so much for WinTalk. The next, .id, which is a decentralized identity protocol. because in the WinTalker system, we need identities. We need different well-known public keys to offer reliable services and to offer the address book for different public keys, so that we will provide identity for WinTalker system and providing a more friendly alliance system that could use phone number and existing email. You can register your phone number and existing email in a global decentralized ID system. And it could be compatible with Paymail. It helps the user, not the private key owner, to own their data. It works without touching the coins. We carefully design the protocol so that the needs for the transaction are minimum. We use transaction ID as the ID identifier. So the DID will look like there is a DID as a scheme and .id as a DID method name, and then followed by the transaction ID, which is the DID method specific string. In the transaction, we will find a way to embed the DID document, the hash of the DID document. We need to use hash because we need to preserve more privacy for the user. Why we need to use the TXID, not use the public key directly? Because we think there will be a lot more advantages using TXID. TXID is globally unique and it cannot be tampered with, and it is very easy to trace. TXID naturally reflects the time of the DID creation. You can change the public key without changing the identity. And the DID status can be quickly determined by UTXO status. These are two basic APIs. One is to get the raw transaction from TXID, and the second one is to get the status of the UTXO to find out if the UTXO is spent or not. So the cost of obtaining the ID document is extremely low. Relying on the public key will bring in higher indexing costs and the overhead of passing the ID documents around. And we have flexible data embedding methods. .id hopes to avoid touching the user's privacy as much as possible. DID identity information and files will be completely saved and controlled by the user itself, not service providers. Users can have infinite DIDs associated with the same VC, which is verifiable credentials. The public key information on the blockchain is only the digital digest and the user's public key, which is used to verify the legitimacy of the file. Using the UTXO model, we can solve the problem of real-time check of certificate revocation. When you revoke a certificate. The CA just spent the UTXO, and the revocation will happen in real time. So there's a DID document creation. First, the user will request UTXO from our BaaS bus system. Bus means Bitcoin as a service. Then the bus system will return the UTXO to the user so that the user can use the UTXO and the public keys and the registration agency's public key to generate a transaction. And the user can send the transaction along with their DID document to the registration agency. The agency will verify the DID document and use the hash to spend the second output of the first transaction. And in the same time, embedded the hash of the DID document into the second transaction. Why we will need two transactions? Because when we need to use the transaction ID as the DID, then we will include the DID into the DID document to make it accepted by the registration agency, so that we have to use different transactions to make it happen. But those transactions are closely connected to each other. When the bus receives the transaction, the two transactions from registration agency, they will assemble the transaction with fee-paying input and submit the two signed transactions to the miner and return with all transactions and Merkle proofs to the user. This is the whole process of the DID document creation. At the end, the user get two transactions. Okay. The first one, we have two public keys that can decide whether to spend the output. And the second output is spent by the CA to provide the DID document. The hash of the transaction 1 is embedded in the DID document and form the DID document hash, which is the output of the second transaction. When we need to validate the DID document, we can check if the first output is spent either by the CA or by the user. And we can still replace the transaction, replace the DID using different public keys in case the user lost their public key and private key. They can request a new one. So the CA can spend the transaction, the output of the transaction 2 to have a new transaction. How to verify the DID document? The user will send the DID document along with the transaction 2 to the verifier, and the verifier will check with the miner to ensure the output 0, which is the first output of the transaction 1, is unspent. Which this is very easy because in the transaction 2, we have the out points to the output 1, which is V out 1. And we can easily point to V out 0. They have the same transaction ID. And the miner will return the UTXO status and the Merkle proof of the transaction 2. The verifier will verify the DID document to match the hash embedded in transaction 2. The DID document is handed over directly from the user to the verifier. And the verifier will verify the SIG and the public key in the transaction 2 to match a valid registration agency so that the DID document can be verified. Then in the DID system, we need verifiable credentials, which is almost the same with the DID document, but it includes the points to the DID. The verifiable credential is the credential that can prove something connected to the DID. Like the when we have a DID that reflects my ID card, then I will have some sort of credentials that proves I'm an adult. Then the CA will provide such kind of proof and using their private key to sign the proof. So it is almost the same with the DID document creation. Their transaction templates are almost the same. And we can use the same method to verify the credential. Okay, so much for the 2 features. If you want to know more, you can go to developers.wallet.com. And the 2 features will be available before Q2 this year. Those specifications may be changed in the future, and we are looking for more collaboration on the 2 ideas. You can get in touch via business@boquaninc.com. That's all. Thank you.
Thank you very much, Lin. And 2 new things that have come out of the woodwork today, Windtalker and a decentralized identity protocol. Both of them look fascinating, Lin. We've got a few questions here, but I'm actually going to begin with one that's more of a comment. Rowan Sharon says that the Windtalker protocol functions just like a signaling server in WebRTC, that's web real-time communications, which connects 2 peers directly. So it can probably be used to create WebRTC connections, which is an interesting observation. That's a fairly base layer function in modern web browsers right now. So that's obviously an interesting item to consider putting on the future roadmap. So Lin, I think we'll dive into the first and most obvious question, which is where can people find the APIs that .wallet provides?
Okay, you can just use developers.wallet.com. And
developers?
Yeah, you can find .wallet.com.
Developers.wallet.com. Okay, cool. And all your API endpoints are available from one place.
Yeah, all the APIs provided by not only the wallet, but also from the mempool. We offer the MAPI access that is already in the developers document section, and you can find the English language switch if you are landing on weird Chinese characters on the left button of the page. You can switch to English version. Yeah.
Okay. And do you have any stats on English-speaking users? Do you get many users from outside of China?
Yeah, we have almost like 2/3 of our users are outside of China.
Okay. Oh, that's great. So our next question is about WinTalker. Someone wants to know if WinTalker messages are actually sent within transactions and are they on-chain transactions?
Yeah, we can choose from that. Basically, I like to reuse the transaction as an envelope to contain those information and messages. Yeah, we can use the N sequence to make it off-chain in a Satoshi payment channel. But yes, we can always use on-chain transactions to make it immutable record, to keep a record on the blockchain ledger. It depends on the purpose of the messages.
Sure. Okay. I think this is another question about routing from Mixup. So this is, I think that's what the name says, MX1Up. I don't know. I can't pronounce some internet handles. Some of them are designed not to be pronounced. So I think this is about the routing. He asks, how does miner N notify Bob? So I think what he means is Alice sends a message which goes to miner A, which then goes to miner B. But how does miner B find where Bob is at that point in time?
Okay, and as the protocol design, we may use a payment channel funded by Bob and the miner B or the miner N. So if they funded the payment channel, they will come later to retrieve or to close the channel, right? So they will have a next connection in the end. so that those messages could be delivered, but we don't find a way to push those transactions. I think it depends on the two parties between miner and or the service provider and Bob. They can find a way if it is a real-time push notification or push services, or they can use a pull strategy to do so. So, yeah.
Sure. Okay. And that's often the difference, but the fundamental difference between the online and the offline use case. But it sounds like you've probably got both covered there. RC asks, does a dot payment channel does this dot payment channel funding need KYC with the miners? I suspect he's talking about WinTalker again.
Yeah,
I think he's asking, do you need KYC with the miners in order to open any of the funding channels?
I think it depends on the logo laws. As a service provider, you should obey the local laws to provide your services, right? So if it is required to have KYC, so you may choose to obey the rule. Yeah, but it is totally up to the choice of the service provider.
Okay, the technology doesn't require it then. Okay.
Yeah.
And jumping on to DID again, where is the DID document itself actually stored? Is it on-chain, or do you need to query some service to obtain it? Because I think you talked about putting the hash of the document on-chain.
Yeah, we put the hash of the document on-chain, and I think the document itself will be a private part that is have to be kept by the user itself or some delegators chosen by the user. So we don't have to put the whole document on chain, but yes, you can do that. Like you can post your picture of your passport on any website like that. But I strongly recommend doing so.
Okay, so this is much like the SPV model where user wallets actually take responsibility for storing their own transactions and their previous transactions so that they can pass them directly to a peer later, yeah?
Yes. So it is designed fully peer-to-peer, and we do not need to rely on certain third parties. And you can always prove that your document is already registered with the hash on the blockchain and with the signature from the validator. Yeah.
Yep. Okay, that's a useful first step in the exchange to be able to at least validate that far. So our last question today is, as a miner, actually I almost asked this question myself. As a miner, are you going to offer the service to users to offer responses to unspent queries? So I think they mean, can I query you to find out if a UTXO has been spent or not?
I think yes. The answer is yes. I think the perspective of a miner to such a UTXO is very important to the ecosystem, and it contains a lot of information. So I think the answer is yes. In the near future, we'll provide and we will propose the query into the MAPI implementation. Hope Shadows, you can let us to make some sort of things.
I think it's actually a great suggestion. I actually had some thoughts about doing this as an event notification because right now we actually have two different types of events that you can subscribe to with respect to a transaction and its life cycle. And MAPI allows you to be notified when a transaction's mined into a block so that you can get the Merkle proof, and it also allows you to be notified if there's a double spend attempt. The missing piece to that puzzle, I think, is to be notified if the outputs of a transaction are spent or even particular UTXOs are spent. I don't think there's anything complex in the Bitcoin model or the implementations, either Bitcoin SV or Terranode that would make that hard to do. But you're simply talking about a query that provides the same information. So I think that's very doable. I will be bringing the MAPI through the TSC at some point in the near future. So it's probably a good place to get that suggestion in. So, Lynn, we've got a little bit more time. If anyone else has any other questions, please do drop them into the chat. But maybe I'll ask you a little bit about what's going on in the BSV world on the other side of the Great Firewall. Mempool, you've been running that since day one of Bitcoin SV. In fact, before day one, even in the lead up. How is mempool operations going, and what innovations can we expect to see from your team on the mining side?
Okay, so as a very dedicated miner, I think we need to make it accepted by our government and under the supervised by our government. So we will try to offer some sort of mining services that is totally legal in China. And yes, and we will try our best to avoid the money laundering using cryptocurrency. Okay, that's what we are trying to do. And I think in the long term or in the midterm, the hash rate plays quite an important part in the not even miner side, but the data services or any Bitcoin SV ecosystem. Because you need to have a significant hash rate to demonstrate that you have very good connection with other miners, with other service providers, right? And it can be easily verified and detected by other peers, other users using the block headers and the miner ID. So I think that our next step will be integrating the miner ID services for a very long term to help the miner to gradually to build their trust with the service providers. And with our expansion in the mining farms and the ASIC running in China, I think we will gradually grow our hash rate share in the short term.
Oh, it's great to hear. I think you hit the nail on the head. One of the real pressing issues, I think, is getting high-speed internet pipes in and out of China so that we can move bulk transactions back and forth. And that's something I'm very interested in, and something I would hope that I'd be able to work with you on in the future. But miner ID is maybe a really sort of key part to building that trust with regulators that you actually are in it to operate legitimately. We've had another question pop through. As an end user, how does one find the closest miner to connect to? Can this happen in a decentralized way? I can probably answer that one myself, unless Lynn wants to jump in. Miner ID is actually designed in part for that purpose. It allows a miner to basically take ownership of their identity, backed by their own proof of work history. And one of the ways that you can use miner ID is by publishing your MAPI endpoints or any other information about yourself as a miner in the Coinbase transaction. And so we're actually working on a feature for a new peer-to-peer message which allows miners or anybody on the network to transmit headers, block headers, along with a Coinbase document from that block and a Merkle proof, which would allow anybody to basically extract miner ID information. So that basically turns miner ID into a service discovery mechanism. But one thing I think I'll ask Lynn's opinion about is a plan that we have to make use of miner ID in Bitcoin SV, which is to provide a feature which we call preemptive block propagation. As it stands right now, when a miner receives a block, it will do the complete validation beforehand. And the reason why it does that is because if it sends an invalid block to one of its peers, the peer will ban it, because the peer has no way of knowing whether that miner actually generated the bad block or whether they're just relaying one. So Lynn, the idea with preemptive block propagation is that if a block actually has a miner ID attached, that we can actually forward that block onto other miners before we even validate it. Do you see that as providing an advantage to miners that are willing to own their identity?
No, I don't think that is a very good idea, because although the miner ID means identity and trust and a lot of like it contains a lot of previous proof of work information, but I still think that we could not do that before we validate the whole block, and because there might be some miner that could be malicious or be controlled by third parties, and if we do not make good validation, that will hurt the network badly, right?
Wouldn't that mean that the miner, that you would hold responsible the miner whose identity was embedded in the block rather than the miner that sent it to you?
I think the miner ID could help that to we as a one like miner miner, I will try to find out how much hash rate the other miners hold, and we can calculate it based on the block headers, right? And then we will devote we will try to divide our bandwidth resources and the priority to send our blocks and the transaction information to better reduce our risk of overrate, right? So if you have significant hash rate connect to the miner ID, then you will have a much better chance to be connected by other miners. And if you do not hold enough hash rate, you might be ignored by other miners. And that forms the small world network, right? So it naturally will push small miners out of the network, and they will be more centralized together to form the small network. And I think it does not stop the competition completely, because we will not blindly trust the miner ID itself. I think we still have to leverage between whether we should validate the transaction, validate the block before we receive a valid block header from a typical miner, a specific miner. Yes, of course, we can accept those transactions and blocks before they send us the valid block header, and that would make everyone much better for faster block propagation and faster validation, right? And that will cost a lot, because we need to connect to different miners and have different version of their Merkle sheet, different version of their blocks, and we should have to validate them all together, right? That will cost much more than today, right? So we should have to leverage between the cost and the benefit. Right.
Yes.
So I think
it's always that trade-off. Okay, we're running short on time now, but Lynn, it's always fascinating to discuss the finer points of mining with you. I look forward to hopefully being able to do it in the same place again sometime.
Cool.
But we'll move on now. We're just going to take a very short break while we get set up for our next speaker, which is Aaron Russell from Kronos Labs. And I'm actually not going to try and guess what he's going to be talking with us about today, because I suspect he's going to surprise me no matter what I guess. So we'll see you shortly. And don't forget to keep an eye on the intermission screen for those airdrops. Okay, we'll be back in a moment. And welcome back. That was a pretty short break. I hope somebody managed to pick up an airdrop if there was one in that time. And next up, we've got Aaron Russell from Kronos Labs, and he has been responsible for quite a few tools and applications in the Bitcoin SV space, including Operate SV, TX Forge, PayPresto. TX Forge was one that particularly grabbed my attention because a library for building and constructing transactions flexibly was something that was sorely missing from the available tool set at the time. And as I've alluded to a few times so far, I actually have no idea what he's going to surprise us with today. So I'll shut up and we'll find out. Take it away, please, Aaron.
My name's Aaron. I'm the founder of a company called Kronos Labs. I built and I run Bitpost and PayPresto, and over the last couple of years I've released dozens of open source libraries and packages that other developers and businesses are using to help build their apps and services on Bitcoin. So if you want to find out more about this, you can go to kronoslabs.net and you can see the things I'm currently working on. You can look at my code on GitHub, and you can follow me on Twitter and Twitch. So I've been invited to come along today, do this presentation, really just to show some of the things that I've released and put out there and explain how you can use them in your apps and projects that you're working on. But I really wanted to focus on one particular thing. So something that I've been thinking about a lot recently, and I've been working on some new ideas. So today I'm going to reveal some new code. I'm going to reveal some new code for the first time, so a bit of a world exclusive, and then I'm going to kind of demo that code and explain how it fits into the apps and services that you're building. But before I get into that and show you what I've been working on, I just wanted to explain some of the context and behind some of my thinking recently. So as a developer, I'm really interested in Bitcoin because I recognize that it changes the nature of the different types of apps and services that we're able to build on the web. And particularly for me, I'm really interested in this notion of interoperable apps, where the blockchain is this kind of single source of truth, and users can control that data, and different apps and services use it in different interoperable ways. And so that really excites me, and I know it excites other developers because I've had conversations with them about this. But truthfully, I don't think we're seeing that many examples of this in practice. Maybe we can point to a few alternative Twitch clients that exist, but I think these are kind of the exception rather than the norm. So I've been thinking about this and wondering why it might be, and wondering, are we thinking about things in the right way, and do we have the right tools? So when it comes to putting data on chain, over the last couple of years, what has become a kind of de facto standard has been Unwriter's Bitcom, which is really just a set of conventions for how we encode data in a transaction. And it's been huge. I don't think we can really underestimate how significant an impact Bitcom has had. It came around at the same sort of time as the op return limit was lifted to 100 kilobytes. And I would say that kind of combination of events was the most impactful event in Bitcoin's history in terms of like new apps and services and this explosion of ideas and development that we've seen. And it's perhaps not the sexiest thing. People look at op return data, maybe kind of like sniff at it a little bit because it's not quite as clever as smart contracts, and not quite as sexy as other kind of things you can do with opcodes and custom scripts. But in terms of impact, Bitcoin has been huge. You can just look at the blockchain for this. Look at, scan the blockchain over the last few years, look at any block, scan through the transactions in any block, and you will see that the majority of transactions are data transactions. They are op return outputs, and the majority of those follow the kind of Bitcom conventions for encoding that data. So definitely it's been huge, and credit where it's due. But I think maybe there are some problems with Bitcom, and maybe it might be time to kind of just have a think. Is this the right way? Is this the optimal way of building? And there's a few problems that I've identified. First of all, Bitcoin, the software, doesn't actually work. And so I should explain by this, Bitcoin is two things. It is a decentralized registry of protocols, of application protocols, and it's also a set of conventions for how we encode data in a transaction. So obviously those conventions work fine, no problems there. But the software that you use to register your protocol, I don't think that's worked for over a year. And so if part of the benefit here is that we have this decentralized registry of application protocols that we can kind of browse and scan, we can find out more, read the specifications and that kind of thing. Well, if that doesn't work, that kind of undermines the point a little bit, in my opinion. Also, I'm going to show you a typical Bitcoin transaction. So what we're looking at now, this is actually a Twetch. This is a great example of Bitcoin. They have piped 3 different protocols together. First one here that I've highlighted, this is the B protocol. So this describes a file, and this actually contains the content of the Twetch. The next bit that I've highlighted here, this is the magic attribute protocol, MAP. So this is like a load of key value pairs of various metadata that Twetch requires. And then this third chunk that I've highlighted here, this is the author identity protocol. So this contains a signature. This is how we authenticate who the author of this Twetch is. So that's all fine, and those protocols are well defined. They've got specifications, we can read them, so we can kind of understand what's going on here. And it's not that hard. We know what all this stuff is, but just looking at it, there's a lot of. There's too much human effort involved in actually creating this transaction. If I want to read a Twetch, I need to kind of deserialize all these different attributes into some usable object for my software. That's a lot of hard work. And likewise, if I want to create a Twetch, I need to take my object in my software and map it into this really quite specific format with pushes of data in quite a specific order. And yeah, it's true, there's a Twetch software development kit which obviously makes that easier, which is great if you're doing your development in JavaScript, but if you're not, you've got to write that yourself. And that's kind of the point, really, that all of these protocols, someone needs to write some code. Everyone that wants to implement them needs to write some code to implement these protocols, and there's a lot of repeated human effort there. And I'm inherently lazy. I don't want to do work that I don't need to do. Next up, this third protocol, like I said, this contains a signature. Now this is the author identity protocol. I think I understand this quite well. I've implemented this protocol a few times in different languages. If you read the specification, there's some test transactions, so you can test your implementation and check that the signatures verify. So I've done all that. I think I understand this protocol, but I can't get Twetch transactions. I can't get the signatures in them to verify in my implementations. So I don't know why this is, and it is either that I have done something wrong, which is perfectly possible, I get things wrong all the time, or Twetch have changed something in their implementation. They've gone off spec slightly, and this is easy to do. When you're talking about cryptography, just one byte out of place, and you've inadvertently just created a new algorithm. And I wonder if maybe something like that has happened. I don't really know. It doesn't really matter whether I've done something wrong or Twetch have changed something in their implementation. The point is that if you're expecting every single participant to implement this, the scope for human error there is huge. Of course things like this are going to happen. It's just too brittle. So I don't think that's a good way of doing things. And the final point I would just make about Bitcoin is when it came out, it sort of went hand in hand with Amrita's other inventions, which was Planaria, and this was mainly how we were building apps at the time. We were using Bitcoin and Planaria, and we had this idea that maybe we could build these serverless applications where we just kind of build a front end and pull data dynamically from these APIs and stuff. You know, in retrospect, sounds nice, but you soon hit reality, and I think we've learned now that if you want your application to work all the time, you probably do need to have your own database. You need to have your own cache of transactions and not really be dependent on third parties in quite such a significant way. And so what this means, if you're creating your own cache and you're storing transactions locally anyway in your own app, then you can create your own indexes and your own search features within your app. So I think this idea of kind of searching and filtering by specific push datas, I mean, it obviously still has a place, but maybe it's not quite as significant as it was a couple of years ago. So I think that allows us to start thinking about new types of ideas, new ways of doing this. So I've been looking around trying to get some inspiration. And so the first thing I looked at was JSON. I mean, how easy would that be? Just to take our data, encode it and decode it. You don't need to encode and decode anything, because that's exactly what JSON is. You would just take your object and encode it into a JSON string and put that in a transaction. I mean, that to me is like, that's as easy as it gets. Now, obviously JSON has a few problems, because we're often going to be working with binary data. We're going to have signatures and public keys, and so we need to encode those. That won't work in JSON, so we need to encode those in base 64 or hex encoding them. So we've got like extra hoops that we need to think about, extra hoops to jump through, and also that's going to increase the size of our data payload. So maybe JSON isn't quite perfect for our use. So then I looked around at the various binary data serialization tools that we have. There's loads of these, and message pack and protobufs seem to be quite popular at the moment. I particularly am fond of CBOR. Now the reason I like CBOR is it works just like JSON. So you don't need to think in terms of creating schemas and structs. You can do that if you really want to maximize your efficiency and save every last byte. But if you just want that convenience that JSON gives you of taking any arbitrary object containing any types in it, and you just want to encode that as a binary, CBOR is absolutely fantastic for that. So I really like CBOR. When it comes to signatures and encryption, I think that should be handled that should be a first-class citizen of our protocol. That shouldn't be like offhand, implemented elsewhere. So we shouldn't be relying on individual users and builders to kind of be really getting their hands too dirty with that stuff. So I again turned to JSON for inspiration, and particularly to a family of specifications which I think are referred to as Jose or Jose or just JOSE, I don't know. I'm going to call it Jose. But this is a JavaScript object signatures and encryption. And if you've come across JSON Web Tokens, which if you've been building on the web, you probably have, JSON Web Tokens are actually a part of the Jose family of specifications. There's like 5 or 6 different specs here, and they describe how you can serialize data, authenticate it, and secure it. So this is actually exactly what we need to do. So this is a really great resource for us. Other people have thought of this problem, and they have solved it. Now, it just so happens that there is a CBOR version of Jose, which might be called Cozy or Cozy, or maybe just COSE, who knows. But I've read all those specifications as well. And I've taken those as an inspiration. So I don't think we need to re-implement all of Jose or the CBOR variant, but there are bits that we can take out. And so that's what I've done. I've taken out what is sensible and I've repurposed that into a new protocol, which I'm revealing today. What I've created is called Universe. It is a universal schema for serializing data with signatures and encryption built in as a first-class citizen of the protocol. So it allows us to serialize any data, any arbitrary piece of data in a concise, compact, binary-friendly format. We can use signatures to authenticate data, so we can use that to help us prove ownership or authorship or the origin of a particular type of data. And finally, we can encrypt that data, so we can ensure confidentiality of the data that we're putting on the blockchain for particular recipients. So that is what I've built. That's what I'm going to reveal today. I'm going to jump in now and show you some code, show you how Universe works and how you can use it in your applications. So to show you how Universe works, I've got a few quick, short demos for you. First up, we're just going to have a look at how we serialize data in Universe. So each of these demos I'm going to do in a web page. The reason I'm doing it in a web page is just because we can log various output to the console, so we can have a look at the different objects we're working with. I can go to the browser, refresh the browser, and look at the console, and we can dive into some of the objects, and I think that's just an easier way to explain some of the things that are going on. But if you are using Universe, you can use it in the browser, you can use it in a node environment, and there's also an Elixir version of Universe for those rare but incredibly wise developers that have chosen to build their Bitcoin apps with Elixir. So let's get started. This is just a blank HTML page. At the top here, we're loading two libraries. First of all, the BSV library, which is dependency of Universe, so we need that. And then we're loading the Universe library itself. When we do that, it's attaching a Universe object to the global scope. And then underneath here, we've just got a script tag, and there's a self-calling asynchronous function. So I've just wrapped everything in an async function because some of the stuff, when we come to do signatures and encryption, we can use the await syntax. I just think it's a little bit easier to follow what's going on then. So first thing that we're going to do is take that Universe global object, and we're going to assign the envelope class from that. Now the Universe object has a few more classes attached to it. Mainly you will work with the envelope class. So that is how you wrap a piece of data. That is how you would sign that piece of data and encrypt that piece of data. We may cover some of the other parts of the Universe object in these demos, but mainly we're going to be working with the envelope class. So in our function, first thing we need to do is define a payload. Now, because under the hood we're using CBOR, the payload can be anything. It can be any kind of data. It can be binary data, it can be an object, it can be a string. So I'm going to create a payload which has got mixed types. We're going to have a property with a string value. Going to have another property with just some binary data in it. Just a few bytes of binary data. We'll have an array and a nested object, and one of those properties will be a number. So we've just got a real mix here of like representing a kind of complex object of mixed types. And then what we next do is we use the envelope.wrap static function. We'll pass the payload as the first argument, and then the second argument is an object containing headers. So this is key value pairs of headers. You can actually set any header that you need for your use case. There are some predefined headers, so that some headers mean something. I'm not going to go into that in this demo because it will take too long, but read the Universe specification and learn what there's a small number of headers that have a specific meaning. In this example, I'm just going to use the proto header, which you can view that as kind of the protocol prefix a bit from Bitcoin world, but it doesn't need to be a Bitcoin address. It can be any kind of identifier that makes sense, just some way to identify what this payload of data represents, what protocol or app or whatever it represents. So once we've defined that, we can now use the log. So let's use console.log. We'll have a look at the envelope we've created, and then we've also got a few functions for encoding our envelope in different formats. We can use toBuffer to encode our envelope as a CBOR encoded binary. We can use toString to encode it as a string, and toScript encodes it as a Bitcoin script. So we're going to do all of those, log it to the console, and we can head to the browser and refresh, and we can have a look, and that there are our outputs. So we can see the envelope. If we drill down into the envelope, we can see that it has 4 properties. We've got the header, the payload, and if we drill down into that, we can actually see our payload. And by the way, with the headers, actually, I should mention that internally the order of your headers doesn't matter. So when we come to do things like signatures, the headers get signed, but the order becomes normalized. So it doesn't matter what order you add them in. When they get signed, they're always in a normalized and consistent order. So we always have consistent signatures. Yeah, and we've got a couple of other properties. We've got the signature property and recipient property. These are undefined, and we'll have a look at what they mean in a few moments. If we look at the outputs underneath, there is our CBOR encoded binary. If you have a look at the string, this looks a bit like a JSON web token, or this is basically where the Jose influence comes in. So the first chunk here is the header, and the second chunk is the payload. And what's happened here is these different parts are CBOR encoded. They are then base 64 URL encoded, and this may be useful if you're sending this kind of data over the web or storing in a cookie or whatever. And then finally we've got the script, and if we can drill into that, we can see the first push data after op return is a prefix, so that is an identifier that this is the universe protocol. The subsequent push data is the header, and then the final one is our payload, and all of this is in a concise binary format. So the envelope class also has corresponding functions to decode these encoding formats. So we have a from buffer, from string, and from script function. So that kind of represents how you would take a payload of data, encode it, send it over a network or put it into a Bitcoin transaction or do whatever you're going to do with it, and then someone else is going to decode that using these functions. So we'll quickly have a go at that. We'll create a second envelope, and we'll use from buffer, and we'll take our first envelope and encode that using toBuffer, and we'll log that to the console. We head back to the browser and refresh. We can have a look at our second envelope, and as expected, it's identical to our first envelope because it is the same. And that really just represents how it is encoded and decoded. So finally, I think we should put one of these on the blockchain. So I'm going to quickly add the money button library to the top of our page and write a little bit of code here. Let's render, we'll add a button element, and we will render money button to that element. We're just going to have a single output, and we will take our envelope, we will convert that to or encode it as a script, and then we will further encode that as a ASM string, which is needed for money button. And then once that payment is complete, we'll put something to the console. So let's quickly refresh that and swipe that button, and that's worked. So now that envelope that we've created is on the blockchain. So we have added something to the universe. if we quickly flick over to this tab, now this is the Universe website. At the time I'm recording this website, at the time I'm recording this video, this website is very much in development, but there is an Explorer and we can see that our transaction there has been added there. So we can see that in the Explorer. So hopefully by the time you see this video, the Universe website will be live and there will be good documentation for you to dive into and read all about this and have a play with the Explorer and see transactions live as they are added to the blockchain. So in this next demo, we're going to play around with signatures. So we're going to just sign a piece of data. We're going to sign an envelope and then verify that signature. So for this demo, we need something else from the Universe global object. We're going to grab the key class and then we're going to use that straight away. But let's generate some keys. So we'll first of all generate a key for Alice. And this is going to be an elliptic curve key on the SECP 256K1 curve, which is the Bitcoin curve. Now in practice, you may well have your own key pairs. You probably will. You'll be using the BSV library and you'll have your own keys, and so that there is a way to convert a BSV key to a Universe key. They're basically the same, they just have a slightly different internal representation. But just for the purposes of this demo, I'm just going to generate some keys using Universe. So once we've got Alice's key, we'll also create Alice's public key, just by converting Alice's key to a public key. And so what this represents, Alice would of course sign her envelope with her key, and then a third party would be able to verify that signature with her public key. We're also going to create a third key. This is just going to be a random secret. So this is not an elliptic curve. It's not a key pair at all. It's just a single sequence of random bytes, 256 bits long. And so the reason I'm doing this is there are other algorithms. We don't have to sign using ECDSA. We can do other kind of algorithms. So, and that's all built into Universe. So I'm going to show you a couple of different algorithms that we can sign with in this demo. So first thing, we'll log all of these keys to the console and then head to the browser and refresh our browser. And so we can see Alice's key there. If we inspect that, there's a bunch of parameters. The D parameter is the private key and the X and the Y are the points on the curve. So that's the public key. And then, so if we have a look at Alice's public key, that is just the X and the Y parameters. The D parameter isn't there. And the secret key is just a single parameter of random bytes. So head back to the code. We're going to define a payload, just a simple payload, and we will wrap that payload in an envelope. We'll just log that to the console as well. And now we're going to sign that envelope. So we will sign using Alice's key. So when we use the sign function, the first argument is the key and the second argument is a set of headers for this signature. So we need to define at the very least the algorithm. So in this case, we're going to use the ES256K algorithm, which is basically ECDSA on the SEP 256K1 curve, a Bitcoin signature. And the second header here, KID or KID, that it represents the key ID. This could be anything. It could be a Bitcoin address, it could be a Paymail address, but it's some kind of hint to a receiving party, a third party, of what key they need to verify this signature. So I'm just going to write Alice in there. So then we can log our envelope to the console. We can refresh the browser and let's have a look. So you might have noticed I logged the string encoding of our envelope twice here. Once before we'd signed it and then after we'd signed it. So you can notice here that after we've signed it, there is another chunk of data in our envelope, which is our signature. So that third chunk represents a signature. And if we browse down, if we drill down into the envelope, we can see that signature is there. That consists of a set of headers, which is the algorithm and the key ID, and the signature itself, the binary value of the signature. Next thing we can do, we can just verify that using Alice's public key. So the verify function just accepts one argument, which is the key that we're going to verify against. We can log that to the console, head back to the browser, and sure enough, we can verify that signature. So everything is working there. Now it is possible to sign many times using, if needed, different algorithms. So the way we do that, and there are lots of use cases for this, by the way, and there are many reasons you might want to sign twice. Your application might want to add a signature so it can verify that it was the source of this piece of data, as well as the author and the owner. You might use signatures like in MetaNet to kind of represent hierarchy and structure. So there's all sorts of use cases for signatures. So we can add as many as we want, and Universe has no limits to the amount of signatures you will add to a single payload. But in this case, we're just going to sign it twice. The first signature will be Alice's. We'll use Alice's key. We'll just sign that. And then the second one, we're going to sign with that secret that we generated. So the way we do this, we pass an array of arrays to the sign function. So for each sub-array, the first element is the key. The second element is the headers. For the second element, the second key here, we're using the HS256 algorithm, which is a hash-based message authentication, basically a MAC, and we'll add the key ID of secret. So we will verify that as well, and we verify the same way by passing an array of keys, and they obviously must be in the same order as the array of signatures. So we do that, we can log that output, head back to the browser, refresh the browser, and would you believe it, it verifies. So that just shows one way that we can sign our envelope with many signatures. So in this last demo, we're going to play around with encryption. So we'll first of all generate a couple of keys. So we'll have our key for Alice, and we'll also create a key for Bob. So both of these are ECDSA keys, because we're going to play around with asynchronous encryption. So in this case, it works the other way around. So we would encrypt with Bob. So if Bob is our recipient, we would encrypt with Bob's public key, and then Bob, as the recipient, would be able to decrypt with his private key. But there are also synchronous encryption algorithms, so we could, if we wanted to, generate a secret. And that there are different use cases for different types of encryption. But in this demo, I'm just going to use asynchronous encryption. So we will define our payload and wrap that in an envelope, and we'll log a string encoding of that to the console. Also, we're going to sign the envelope with Alice's key. You don't have to do this. It's not necessary that you must always sign it as well as encrypting it. You could just encrypt it without the signature. But just for this demo and for completion's sake, I'm going to sign it with Alice's key, and we'll log the envelope encoded as a string to the console and the payload. And then next up, we're going to actually encrypt. So we use the encrypt function. So as with the sign function, the first argument is the key. So in this case, we'll use Bob's public key because he's our recipient. And then we must provide some headers. So we have to give the algorithm. So this is a complete mouthful, but what that is a ECDH key exchange. It uses a KDF function to derive a secret. And then that secret is used to encrypt the payload with the AES-128 GCM algorithm. And the key ID in this case is going to be Bob. So Bob is a recipient, he knows he can use his key to decrypt this. So we will log this now, the encoded envelope. We'll log the payload and the envelope itself to the console. Head back to the browser and let's have a look at see what we've got. So we can see here we've logged the encoded envelope a few times. So the first time we see it, this is just two values, the two chunks. We've got the headers and the payload. Then we signed it with Alice's key. So we've got this third chunk. So that's our signature. And we can see the payload here is still unencrypted. Then we encrypted it with Bob's public key. And so now we can see the encoded envelope has a fourth chunk on the end of it. So that is now complete. And if you're really eagle-eyed, you'll notice that that second chunk is different than in the previous two logs, because that is the payload and that is now encrypted. We can see underneath that that payload is now encrypted. It's just a bunch of bytes. And if we drill down into the envelope itself, we can see that those four properties, the headers, the payload, the signature, and the recipient all now have values. We can have a look at the recipient and see that that is a set of headers. It also has a key property which has nothing. That comes into use when we encrypt for multiple recipients, which is possible, and one of the features built into this. I'm not going to have time to demo that in this presentation because I'll need another 10-15 minutes to do that. But for now, let's head back to the code, and we can decrypt this with Bob's key. So yeah, we just use the decrypt function, pass in the key, and we can log the payload and head back to the browser, refresh, and sure enough, our payload is decrypted. Like I said, it is possible to encrypt for multiple recipients. I don't have time to fully demo that, but the way it works in principle is when you pass an array of keys to the encrypt function, the first key is used as the content encryption key. And so that is used to encrypt the payload using the specified algorithm for that key. And then each subsequent key is used to encrypt the first content encryption key. So at the receiving end, the recipient would use the envelope decrypt at function, the first argument of which is the recipient index for that key. So that is Universe. You can find out more at universe.network. You can read the documentation, you can read about the specification, you can find out about the JavaScript and the Elixir libraries, and you can discover all the algorithms that you can use for signatures and encryption. I encourage you to have a play, try it out. If you have any questions or any problems, please do reach out to me. Thank you.
Well, thank you, Aaron, for a very comprehensive display and probably one of our first really deep dives into some live coding. For anybody who is watching that may want to review it again, it's always easier to watch these code demos when you can pause and control the pace. These videos will be made available after the DevCon is closed. There was a lot to digest there. So thank you, Aaron. Before we get into the Bitcoin questions, I have to ask, is that a pair of SL1200s on the shelf behind you?
It is, yeah. Dating back from the 90s, and they work as well as they did then.
They are an amazing piece of machinery, and you've just made me homesick because I have a storage shed back in Australia with a pile of records about that size and a few of those. Okay, well, let's move on to the Bitcoin business. This is fascinating because we actually tried to solve exactly the same problem a few years ago for MAPI. If you're familiar with it, MAPI responses can be signed by miners, and we had to deal with the problem, how do we ensure that there's a canonical representation of JSON? At the time, we looked around for standards, and the only ones that we did find were still a bit fluffy and in draft form. So we came up with a solution which solved the problem, but probably wasn't the most elegant of solutions. So I'd be really interested to take a much closer look at this. So my question to you is, are you planning on supporting this in any other languages?
I personally have released it. I've released 2 libraries today, a JavaScript library, which works in the browser and Node. And I've also released an Elixir library because I do lots of development in Elixir. I personally don't intend to write any more implementations, but I have published a spec, and if no one else wants to, then I'd be very pleased to see that.
Sure. Okay. Well, we'll definitely look into that as an option for maybe a future update of Mappy. I share your fondness for CBOR for probably largely the same reasons. And of course, the question that was inevitably going to be asked, is there a link to the site?
Yeah, so I announced this only an hour or 2 ago. So you can head to universe.network, watch the spelling in universe, because I've clearly spelled that wrong. So it's universe without an E. Yeah, so on the website, you'll be able to find an explorer, which has got a kind of, it's a very basic feed of all transactions that are being put to the blockchain using the spec. And then there's also a set of documentation, which explains, the ideas behind the spec, and also, an intro to the 2 libraries, the JavaScript and the Elixir libraries.
Okay, so that's universe without the E .network. So go check it out and take a look. I can think of 1,000 different applications for a library like this without even having to try. So if you're thinking about building a Bitcoin application, this could end up being an essential piece of your toolbox. So we do have a question about JSON. JSON has been shown to have vulnerabilities due to the many different types of JSON parser specs in use today. Does CBOR have similar issues?
I don't know, is my simple answer to that. I mean, the CBOR specification is stable and standardized. And so really this comes down to the implementations of that specification. It's perfectly possible that, certain implementations might be different from other implementations. I don't really know, but I've not encountered any issues with the work that I've done with it so far.
Sure. Okay. I think in a form as widely used as JSON or CBOR, that if there are issues, they're probably going to be relatively well documented. So it's probably only a few Google searches away. And JW asks specifics, I guess, of the protocol. Does the proto header have to be unique, like it is in Bitcoin?
No. So according, the advice that I would give is no, it doesn't have to be. It's up to you. You can put whatever you want in there. There are no hard and fast rules about that. It's really just a header that is designed to allow you to kind of identify a transaction that may well be relevant to your application. But yeah, there are no rules and no registry of protocol headers. But it would make sense to, if you're creating an application, it would make sense to use a unique protocol header.
Identifier. Yeah. Okay.
Yeah.
Now, you mentioned earlier in the presentation that you thought that encryption should be a first-class citizen of Bitcoin-like libraries. Do you think that we should be writing our own implementations of these, or making use of tried and tested cryptography libraries, even if that means it's not entirely as Bitcoin-like as we would hope?
Well, I mean, what I've done with Universe, I certainly haven't written dived into the maths and implemented the encryption at that level. I have used tried and tested specifications and algorithms. So I've taken the Jose set of specifications, which has dozens of encryption algorithms, and they're really well documented. So I've used that as a resource. So Universe comes packed with a handful of those algorithms. And then in addition to that, I've added in a couple of Bitcoin specific algorithms. So when it comes to encryption, I've added in the ECs, the Electrum ECs, algorithm, which is kind of commonly used in the wallets that we're using. And also with signatures, I've added in the Bitcoin signed message algorithm. So that's really just to provide a bit of compatibility with our existing tools.
Yeah, sure. EC is, I think, also known as ECIES. So I've never actually had a voice conversation about it, so I've never resolved whether you pronounce it one way or the other. Another question, why are different algorithms specified by strings instead of constants to prevent mistakes? How would you go about finding out all the available algorithms?
I'm not entirely sure what that question relates to, but yeah, you identify the algorithm by the alg header when you're using encryption. But yeah, if you head to the documentation, there is a list of supported algorithms that I've built into Universe. And it doesn't need to be limited by that. There's like I say, if we use Jose as a reference, there are dozens more algorithms that we can add in.
It's actually quite common to reference crypto algorithms using strings. I have to deal with it in Java all the time, which is, yes, I admit it, I'm still using Java. Degan would like to make the comment, amazing work, Aaron, beautifully done, which I think is pretty fair sentiment. We've got a few more questions, but we are running a little short on time. So we're going to pass those on to Aaron and see if we can get him to write some responses that will get published. We have had a few questions through the day from people who are asking a little bit of a bit of background on Bitcoin SV and what it actually is. So that would lead me to believe that we've got some people in the audience that are new to Bitcoin SV. I could answer the question, but I answer this question a lot. I might actually throw this one back to you, Aaron. How would you define what Bitcoin SV is?
I would define Bitcoin SV as Bitcoin as originally intended, as originally envisaged. Simple as that.
That cuts to the heart of it. I'll add to that by saying that Bitcoin SV actually shares a lot of the history with Bitcoin BTC and BCH. We took a lot of people collectively took a decision back in 2018 to attempt to restore elements of the protocol, which basically put us out of consensus with Bitcoin Cash and resulted in two versions of Bitcoin going forward. And so we've continued that process of scaling Bitcoin up the way that Satoshi Nakamoto described and intended, and restoring elements of the protocol that have been changed over the years because as we discovered when we did the analysis, most of those protocol rules were actually there for very good reasons that really facilitated some of the scaling capabilities of Bitcoin. So we're going to have to leave it there because we've run a bit over time and we're due to start our next presentation in about a minute. And we've got to get set up. So thank you very much, Aaron. That was a fantastic presentation. And I guess you can rest, relax, and go spin some tunes now for a while. We'll be back in a moment, or you'll have to plug it back in first, I suppose. We'll be back in just a moment with our next presentation. Welcome back. It's now time for a double act, starting with an in-chain double act, followed by another in-chain single act. I'd like to introduce Jack Davies of MetaNet fame and Alessio Pagani from our in-chain research team. They're going to be talking to you today about Bitcoin transactions, methods of embedding data in Bitcoin transactions, and a few different ways of actually constructing Bitcoin transactions. So coming from one of the people who worked at the heart of the MetaNet team, which is, of course, one of a very interesting way of making use of data on chain. We are definitely in the hands of experts, so I look forward to seeing what Jack and Alessio are going to show us today.
My name is Alessio Pagani. I am a researcher at nChain, and today with my colleague Jack Davies, we will present Bitcoin data transactions and how to use them for your data. During this presentation, we will show the Bitcoin transaction format, we will discuss how to embed data in our transactions, and we will present some data protocols and some data structures. So if we want to create a data transaction, the first question is, how do we create a transaction? So how can we create ledger entries in Bitcoin? So before talking about data, we will talk over the transaction format, we will inspect a transaction in JSON, we will briefly discuss Bitcoin scripts, and we will also create a transaction using the Bitcoin client. The primary functionality of a Bitcoin transaction is to transfer custody of Bitcoin from one to another. We can see in this slide the most important fields of our transaction, but for the sake of this presentation, it's important to notice that each transaction always has a list of inputs and a list of outputs. Each input has a reference to an output from a previous transaction plus a script, while each output has always the value being transferred plus another script. A script is essentially a list of instructions that describes how the next person wanting to spend the Bitcoins being transferred can gain access to them. In general, the script in the input is called unlocking script, while the input in the output is called locking script. Scripts are important for us because, as we will see shortly, they will help us to carry data. So you can think of transactions as packets that we will use to include our data. This is an example of a real transaction in JSON format. These views can be obtained from Bitcoin CLI or any other explorer, such as what's on chain. And here we can see all the fields that we discussed before, including the list of inputs in the vin and the list of outputs in the vout. I would like to focus on the vout, so on the outputs. And as you can see, we have a field called script public key. And here we have our output script or our locking script that we will use to embed our data. Note that these JSON representations often include some metadata which are derived from the transaction, but they are not strictly part of it. An example is the transaction ID. Another example is the ASM of the, for example, script public key. The ASM, so the assembly representation, is not part of the message, but is derived from the X representation, which is the one that is actually part of the message. Now, a quick focus on scripts. As we said, scripts are a list of instructions that describe how a person that wanting to spend Bitcoins can gain access to them. The most common public script is the pay to public key hash. Here we have a public key hash in the locking script. And if we want to spend them, we have to provide a signature in the unlocking script. We can have more complex portions of script if we want to achieve additional functionalities. For example, we have hash puzzles, where in the locking script, we have the hash of a secret. And if we want to spend it, we have to provide in the unlocking script the entire secret. We also have R puzzles, where there is a secret that is in the same form, mathematical form of a Bitcoin private key, and it must be known by the spender. We can quickly get to very large scripts where we might want to abstract away. An example is the op push transaction, which works as a pseudo opcode, which pushes the current transaction into the stack. This is an example of a very complex script with hundreds or even thousands of opcodes. This is used to create a very complex behavior, or maybe a smart contracts. Now I will hand over to my colleague Jack that will show you some demos. Over to you, Jack.
Thanks very much, Alessio. Yeah, so I'm going to give a very brief demonstration on how to use the Bitcoin command line interface, or Bitcoin CLI, to generate transactions. So on the left here, I've got Bitcoin D running in the background, and then I've added a few users for the demonstration as nodes. So we've got Alice and we've got Bob. And then I just use the list unspent command to generate this address array here for Alice's unspent output addresses. And then I've also generated a fresh address for Bob using the get new address command. So now if we want to send money from Alice to Bob, then all I need to do is use the send to address command. So if I move down here, we want to send to Bob from Alice. So I'll choose data equals Alice. And then I'm going to use the send to address command. And then I need to pass it 2 arguments. So I need to give it the address we want to send to, which is this we just generated, and then pick the amount. So let's say 5 Bitcoins will send. Then when I hit enter, I get this TXID come back. So this is basically confirming that we've just generated a valid transaction. I'm just going to install this in our generated TXID field on the right here for reference later, so we can check that everything's worked correctly. So the next thing we can do is make sure this is, a valid transaction by mining into a block. So again, if I use the CLI, and this time, because I want to add a block to the kind of reg test network we have here, then I choose the data series network and I generate, let's say, 1 block. It's all we need really. Then we get this block generated here, and this is the block header hash that we've generated. We can actually go and inspect that using another command. So Bitcoin CLI. Again, still, we can look at this as the network as well. And then I want to get block based on that block hash that we've just produced. And the result is this. So you can see here in this TX structure, we have 2 transactions. One here is the Coinbase transaction, which we'd expect to always see in a block. But then we also have this other transaction, which looks like the TXID that we generated. So that's good. I'm just going to add this again for reference in here so we can check this in our program after, but we can already see it looks the same. Then now we've got that transaction ID, we can go and inspect that transaction to see exactly what it looks like. So I can use a particular command. This time I might look at it from the perspective of Bob, because he was the receiver. And I want to get the raw transaction first. So I want to get, what is the raw transaction data that's underneath this TXID. And I get this back. So this large hex string here. So again, copying that, we can use that. We can use another command to decode this. So once again, let's still act as Bob. Then I use decode or transaction this time. Paste in what we just found, hit enter, and then we get this, which is much more friendly. So we get this this large JSON representation here. Now I'm just going to quickly copy and paste this over to our workspace on the right. There we go. Just get the whole thing. Oops, that's easier. Okay. So if I copy and paste this over into our program here, and I will just close it off so it's not getting in the way too much. So we're just going to store that information here for later. But if we just have a quick look at it on the left-hand side here, we see there are lots of fields, as Alessio mentioned. We get the JSON representation here, including the input structures, the output structures, and we can actually see that the address we generated for Bob, MPCS, so on, is in this second output here. So that looks how we expected it to look. So now, what I'm going to quickly do is, based on how that data we've taken, I'm just going to quickly run our demo program here. And what we expect to see is, so we're checking if the TXID that we generated first is the one that made it into the block. So generated TXID equal to the block TXID. And also I've added an extra check here to check that the address in the output that we expect to be sending to Bob is actually that address we generated for Bob. So when I run this, we expect this to be true. And there we are. So we've got the correct transaction ID and the correct address in both places. So that's a simple example of how you can go ahead and make transactions using Bitcoin CLI that will work as expected. Okay, so now we've seen how to create basic transactions using the command line interface. We can now look at how we can embed data with our transactions, and specifically how we can use those transactions as message envelopes effectively, and particularly the scripts within them to carry and embed the data we need for our applications. So I'm going to be covering the kind of key fundamental concept of data pushes, and this is how we can embed any piece of data within one of our transaction scripts. Then I'm going to look at some data carriers, which are scripts or transaction patterns, which we can commonly use to embed data with certain properties associated with each. And then finally, Alessio is going to take you through a demonstration of how you can actually begin to use the Money Button JavaScript library to embed data within your transactions. So firstly, data pushes. This is what we mean when we talk about putting data in scripts. We've already seen two examples of this already, or many examples in the previous scripts. But here I've got on the left-hand side of the bar is the unlocking script, and on the right-hand side of the bar is the locking script for a simple page public key hash transaction. So this is something we've met already in the talk. And highlighted in blue are all the data pushes. So these are all parts of the script that are actually just pieces of data that get pushed to the stack during script evaluation. And so when we refer to data in scripts, we use this term push data, and there's a specific encoding associated with that. So in this case, our pub key hash is actually not just a pub key hash, is actually prepended with its length. So here we have prepending is the hex data 14, or in decimal 20, and then we have 20 bytes of hex data, which is the actual pub key hash itself. So this is what we refer to as push data encoding generally, and when we write this down, we can also use the angle bracket notation above to mean the actual hex data prepended with at least the length. So this is actually what it looks like in the full script. So the rest of the script obviously is these opcodes, which have hex codes surrounding our pub key hash. And we can actually see that the pub key hash, so the data part of this, makes up the vast majority of the script. But there are actually lots of different variants of push data encoding. So what we saw there is this first row example, where we actually only had 20 bytes of data being pushed to the stack. So we didn't need a specific opcode, we could just prepend it with that length. And the examples on the right-hand side, you can see the ASM notation, and then just prepending in red with the length in hex. When we have longer and successively longer data pushes than this, we need to invoke one of the push data opcodes. So these are special opcodes in Bitcoin script that is designed to push data to the stack. So push data 1, this has the hex code 4C. So whenever you see this opcode in script, it's followed by a 1 byte length identifier and then the actual hex data. So on the right hand side here, again, you can see a slightly larger push this time. Gets prepended with the push data opcode 4C, then the length 5E, and then the actual data itself. A similar thing happens for push data 2 and push data 4, the main difference being that in each case we always have the opcode, so 4D or 4E, but then followed by the 2 byte length identifier in the push data 2 case, or 4 byte length identifier in the push data 4 case. And at the bottom, you can see this general kind of conversion from the assembly representation. So we could have just the data hex, and this is what you see in the previous demonstration, where we actually look at the ASM format of the scripts in the transactions. But what's actually in the serialized version, so we switch between the serialized and the ASM format in that script in the demonstration, is actually the opcode and the length getting prepended. So this is something to be aware of when we're thinking about it. And push data 4 actually has an upper limit of around 4.3 gigabytes. So that's kind of defines the maximum size of a single data push you can have in a particular script. So a few important things to note about data pushes. So these are privileged in a sense because they can go in any script. So post Genesis, only constants are allowed to be pushed to the script in an input script, which means that you can actually have data pushes in inputs and outputs, whereas you can't necessarily have other opcodes everywhere. So again, push data is being allowed in unlocking script, and that's what we saw with the signature in a public key hash transaction. We already know we have push data in unlocking scripts there. and there's not necessarily a limit on the number of pushes you can have per script. So you can have many of these. The limits then become about the size of a transaction overall. And you can see here many different applications have been using different embedding methods, adding data to the blockchain over time. Okay, so then data carriers. So now we know how to encode a single kind of portion of data within a script. We can think about the ways we can actually form scripts to do this for us. So the first is just general spendable scripts, and this is the kind of thing we've seen already. So we could add a data push followed by an op-drop opcode to any script, and this would not change how the script runs necessarily, but it would still embed that data within it. So that's one example of adding data to a spendable script. Then we can also have what's called now the unspendable op return, or false op return, or false return, where we have an unspendable script essentially preceding our data push. So here we have those two opcodes, false op return, followed by the data, and we could have many pushes, of course, after op return. But we could also do have a spendable op return script. So here we place maybe a full spendable script that precedes our op return, and then our data comes after that. Again, we may have many data pushes, and these are three kind of general methods you can use to embed data. The main difference between the unspendable and spendable op return, of course, being that there may be more of an incentive for a miner to keep your spendable op return, given that it will be part of the UTXO set, but it's also, of course, not a guarantee. So again, some important things to note about op return. So the whole kind of purpose of op return is that nothing actually gets executed in the script engine that follows an op return. So actually, there's not necessarily a need to format the data that follows an op return in a particular way. It doesn't have to be valid under the script engine rules. However, it does actually use what we call this push data element framing. So what we just referred to in the previous slides, where we looked at how we encode lengths of data. We still do use this convention in Bitcoin script generally to help parsers understand where different pushes are coming in to a particular script. And again, as I said, we can have these pushes part of spendable or unspendable scripts, and there are different properties associated with those. So now I'm going to hand back over to Alessio, who's going to show you how you can use the Money Button JavaScript library to build applications with data embedded in transactions in a more user-friendly and much more scalable way than just doing things with a command line interface. So Alessio, if you want to take it away.
In this demo, we'll see how to use Money Button 1.5.4 to create a Bitcoin transaction. The first thing that we need to create a transaction is a private key, and in MoneyButton.js, it could be created using from random. If we want it for the mainnet, we can use the from random method. If we want it for the testnet, we can use from random, but using the string testnet as a parameter. Another way to have a private key is to import it. So in this example, I'm importing a private key that I already have. And then if I execute this demo, I can see that I have the two randomly generated private keys. I have my private key, and for each of them, I have the address derived from them. If I go on What's on Chain, we can see that I already founded this address with using a faucet. So if I have a look at it, we can see that we have a balance of 0.1 BSVs, and those BSVs are in this transaction received from the faucet. So if I want to spend this transaction, I have to reference this transaction ID, so 1788, etc., and then the exact index that I received. So in this case, it's index 0 because this is my address. So I can create a UTXO using those parameters. So if we have a look at our demo 2, we can see that I'm creating a new object, which is an unspent output, where I reference my transaction ID, 1788, etc., output index 0, and then the other parameters, such as the address, script, and the 10 million Satoshis that I'm spending. If I execute demo 2, we can see that we have my new UTXO object, or the JSON version of it, if we have to have a better look at it. Now that we have our UTXO, we can try to spend it. And so to spend it, we have to create a transaction. This is done in BSV using the method bsv.transaction. We can fund it using the UTXO that we just created, and then we can pay a receiver. In this example, the receiver is created randomly, so I have a random testnet key, and I also have a change, again, created randomly. I'm paying half of the original amount to the receiver and the remaining to the address. If I execute demo 3, we can see our transaction. In this case, it's still unsigned. So this means that I have the transaction, but I cannot broadcast it because this is just created and anyone could spend it. It's interesting to notice that the half of the Satoshis are going to my to the receiver address, but the change is a bit less than the other half because there are the minor fees taken into account here. So as I said, now I have my transaction, I have to sign it. There is a method in MoneyButton.js that is called sign that, using my private key as a parameter, allows to sign the transaction. Why my private key? Because it's the one that I use to generate the address, which is associated with this transaction. So if I execute this demo, we can see that we have now the signed transaction. This is the JSON representation, and this is the raw transaction. We can see that this was the before the signature, and after the signature is basically the same script, but with this signature appended. I can copy and publish my transaction, and a way to do it is to go on what's on chain, broadcast transaction. I paste my raw transaction here, and if I click, I don't broadcast it because I'm sending Satoshis to random addresses, but if I click on preview, we can see that we have our original transactions, the 1788, etc., with 0.1 BSVs, and half of them are sent to the receiver, and the remaining are back to me as a change. This is a way to create a very simple pay-to-public key hash transaction, but we can do even more complicated things. An example is, instead of using the pay-to-public key hash, is to create my own locking script, for example, using this method from ASM, so creating an assembly version, so a set of opcodes that generate my locking script. These are just some random opcodes, but if I execute the demo, you can see that this is my new script with some, of course, randomly generated opcodes. We will use this method for the remaining of the demo. We just saw how to use MoneyButton's BSV library for backend development, but JavaScript is very useful also for front-end development. And here we embedded the same library in this very simple HTML page, and we will use it to create a transaction with some complex locking scripts, and then to broadcast it to the blockchain. So we start by importing a wallet using the WIF private key. So we generate from the WIF, we can generate the public key, the address, and we can also import the UTXO associated with this address. So if we check, just to be sure on what's on chain, this address, we can see that the balance is the sum of the UTXOs available to spend. This is a very simple page, so we can spend only one UTXO. So let's say we want to spend this one, and we start to create our transaction. So we start with the first input, which is the one that we just selected. So we have the script public key, the transaction ID, the index, and then the amount of Satoshis. Then we can start to create our outputs. So the first one, it's a simple pay to public key script. So we can send all the Satoshis to this in this UTXO, in this login script. So we can send all the UTXOs less the fee for the miner. In this case, it's, for simplicity, a basic 1,000 Satoshis fee. We will send it back to our address, again for simplicity, but you can pay whoever you want. And then we have two other outputs. One, it's an unspendable output, and the other one is a spendable output. And we use them to embed some data. In the first example, we have, this is the X for hello world, or unspendable hello world. And here we have the same string, but this says spendable hello world. To the spendable one, we associate also some Satoshis, and we can generate the raw transaction. Of course, if we change something, the transaction will change, or if we change the amount that we want to send. Then this output will be collected by anyone. We generally want to avoid that, so we will send also this transaction back to us. So instead of opt through, we'll add our pay to public key to ourselves. We generate the transaction, then we can copy the raw transaction and broadcast it using Watson Chain, for example. So we have a specific tool on Watson Chain, broadcast transaction. We paste the raw transaction and we can broadcast it. Let's see. Okay, successfully broadcasted. It's still on the mempool, of course, but if we analyze the transaction, we can see that we have one input, the one that we chose, and then we have one, the first output is our pay to public key to ourselves, and then we have the unspendable output. As you can see, it's 0 op return and the X, which is unspendable hello world, and then we have the same but with the spendable hello world and the script that allows us to collect the same the amount of BSV that we associated with this locking script. We can check back our address to see that the transaction has already been included. It's still unconfirmed, so the balance is not updated, but we can see that we spent 998,000 BSVs and we received 997 BSVs. In the last part of our presentation, we will see how to use data protocol and how to use our data transactions to create some application-specific content. We will start with an overview of some BSV data protocols, and then we will see a quick demo on how to use the BitSV Python library to create an application. Many different data protocols now exist. These are some just examples. We have B, we have AN, which are protocols used to store and reference data on the Bitcoin blockchains. We have the Metanet protocol, which is a layer 2 overlay protocol that defines a method for creating data structures over Bitcoin. We have RAN, which is a platform used to build applications and tokens on Bitcoin. But for the remaining, for the sake of time, for the remaining of this presentation, we will focus on the B protocol, which is a protocol simply used to design and encode files on the blockchain. This is an example of the B protocol. The top shows the syntax of a B protocol output. Typically, it follows an op return, but it could be either a spendable or an unspendable output, as we saw in the demo before, and you can choose the one you prefer depending on your specific application. The bottom shows an example for encoding an actual image. As you can see, the first parameter after the op return is a string. This is a constant, it's publicly available, and it indicates that we are following the B protocol. After that, we have the actual file, so in our case, an image buffer. Then we have the media type. So for our example, image PNG, we have the encoding, binary, and then we have the file name, .png. Both the encoding and the file name are optional, so you don't have to use them if you don't need to. And this is an example of an image uploaded on the blockchain and encoded using the B protocol. This is then displayed using the BitFS service. So the on-chain B encoding within the transactions tell the off-chain service, so our BitFS service, how to parse and display the image from within a web application. We can use many protocols in conjunction with one another by layering or chaining them together. In the example shown, we have the B protocol, the D protocol, and the BCAT protocol all together and structured using the Metanet protocol. Each circle here is a Bitcoin transaction, and each will contain an application protocol and the encodings that allow an application or a service to render the data correctly. It's now time for our demo. We will see how we'll write a simple application that writes a file to the blockchain and reads it from the blockchain using Python and the BitSV library. In this demo, we will see how to embed a file in a transaction following the B protocol. We are using Python and the BitSV library, which allows to create and publish transactions. So it's very similar to what we saw in the previous demo, where we created a transaction, serialized it, and then broadcasted it using the Watson Chain API. But here, everything is done automatically. So we can import our wallet as before using the with private key, and then we can embed our file. So the BIP protocol is composed of 4 fields plus the protocol prefix. The protocol prefix is a constant and it's given by the creators of the protocol. And then we create our array with our information. So the first element is the image. So the first apart from the protocol prefix. We have the image, which is loaded and encoded in base 64. Then we have the media type, in our case, image JPEG. Then we have the encoding, so base 64, and then the file name. Then we call this method provided by BitSV, which creates an unspendable transaction using op_return, and then append all the information after the op_return. If we execute it, we have, as a result, the transaction ID of the transaction just created. So we can copy it and check what's happening on what's on chain. What you can see is that, of course, the transaction is still unconfirmed, but we have our script with the false op_return and all the information about our file. What's on chain already detected that it's a Bitcoin protocol, so it follows the B protocol because we appended the B protocol prefix. What can we do with this transaction? The more trivial thing is download it. So imagine now we are on another laptop. So let's restart our kernel. And of course, what we can do is paste our new transaction and download it. We use the API from What's on Chain to download it. And the result is similar to what we saw before. So it's a JSON object with the transaction ID, the inputs, the outputs, and of course, the information that we appended after the return. What's on Chain is quite smart. It did part of the job for us. So if we take the part of the JSON where we have the op_return, we can already see that it already detected that it's a Bitcoin transaction that follows the B protocol, and it already split it in part our file, our information uploaded. So we have the file, we have the type, the encoding, and the name. So we can write it on our hard drive and see how does it look. Here I appended a dash blockchain to the file name just to distinguish it from the original one. And if we execute this function, we can see that we have a new file just downloaded from the blockchain. It is exactly the same as the one that we uploaded, of course. We can do also more complicated stuff. As an example, if we go back to the demo that we created before, one thing that you didn't notice before is that this image is actually a Bitcoin transaction. We can inspect it, and you can see the ID is actually a Bitcoin transaction. You can look at it on What's on Chain, but we can also do something more interesting. So we can take the source code, change the ID of this image, paste the one that we just created, save it, of course. And if we refresh the page, we have a new logo for our page. And this is a Bitcoin transaction that follows the B protocol. What's happening under the hood is basically that we have a jQuery function that iterates on all the images, as you can see, query what's on chain using the ID of the object, of the element, and then it sets the source of the element as the image that it just downloaded from what's on chain. This is the end of our presentation. We saw how to create Bitcoin transactions that carry application data. We discussed many different ways to embed data. We saw different protocols to embed data. And we also saw how to use some libraries that can be used to construct app transactions. We saw the Money Button JavaScript library. We saw the BitSV Python library. I hope you learned something, and thank you very much. Ciao.
Thank you, Jack and Alessio. We've got a few questions for you today, but this is a kind of a low-level topic, so we could branch off in a lot of different directions here. But let's start with the first question, which is, you've shown us different mechanisms of putting data on chain. What is the impact in terms of minor pruning of putting data in transactions using those different methods?
Yeah, so I'm going to answer this one. So yeah, as I say, there's a few different methods you can use, as we mentioned, the spendable and unspendable versions of op return, for example. I think the main thing to say is that if your script is spendable, and again that could be via a particular branch of that script, then I guess that makes it more likely that your transaction output will be stored somewhere by some node on the network. Obviously, I don't necessarily recommend using Bitcoin as like the only storage layer for your application, but I think it's all a game of probability and incentives. So if you make your script prunable, i.e., couldn't be spent in the future, then you're making it less likely that it might be kept, and vice versa. There's kind of a use case for using those two different methods, I think, for that reason.
So I think it's probably quite common to assume that if data is put into a spendable output, that miners have no choice but to keep that in the UTXO set. What would be the potential impact on a miner if they had pruned that data and someone then spent it later on?
Well, I think, yeah, you've got obviously from the perspective of a miner, then there's money on the table, I guess, that they might not be collecting in terms of transaction fees. They're limiting the number of potential future transactions that they can mine. It's kind of at their discretion what transactions they want to mine anyway. But yeah, that's one thing I'd say. You'd expect it to be picked up by someone, and if you're a miner, then that's a competitor, someone you're trying to compete against normally.
And what if you don't actually have the ability to validate that transaction, but it gets mined into a block? Would you, as a miner, then be in a position of having to potentially even pay another miner to send you that data so that you could validate?
Yeah, exactly. I think anything that might hinder your ability to validate incoming blocks that mined by other miners, you're right. That would be another effect of that. Yeah.
Yeah. Okay. So there is a powerful incentive for them to hold on to it. And I guess on a similar issue, someone's asking if you can add Satoshi value to data outputs. I think they mean false op return, as in, or no, they might mean any different type. But yeah, can you add basically value to data outputs, and what would be a use case for that?
I think an example of that could be if you are paying for a good or something, or at the point you can add some data like the receipt for that, or any information for the shop where you're buying. So when you send some BSV, you can attach some data because you want to provide or prove something, or maybe add your name or add an image, if that could be useful. So in any transaction, when it could be useful to not only send money, but also add some information, some data, those could be all use cases where you can create a data transaction with some value, some Satoshi in it.
So that kind of turns it on its head. The transaction may not actually be about the data at all. The transaction might actually be primarily a payment, but you just want to add data to that for some reason. Okay. In the Bitcoin CLI part, somebody noticed that you made a block using a generate command. They'd like to ask how that works.
Yeah, I noticed another question just asking generally about the command line interface. So maybe I can explain how you can use that. So you can download the node software, I think from Bitcoin SV.io, and there's explanation how to install that particularly easily if you're on a Linux machine, and you can run that in what's called reg test mode or regression testing. So you're effectively interacting, or you can kind of set up. So for that demo, I set up a kind of a toy network with Alice and Bob, and then you also have this view from the perspective of the network. That was one of the data directories. And one of the commands you can use there is obviously to generate a block. So this is kind of simulating what the nodes would do in a Bitcoin network. They can collect transactions into blocks. Obviously, it's simplified in the reg test mode, and we're not, there's no proof of work involved. It's just kind of it's generating the block based on whatever transactions you've made. But yeah, downloading and using the node software just for kind of getting used to all those concepts we talked about today, and just kind of getting your hands dirty and inspecting transactions, playing around with them, making things by hand, changing scripts by hand and things. I think that's a really good way to learn about the basics if you're new to it all. So yes, that's definitely something I'd recommend doing if you get the chance.
Mm-hmm. So maybe they thought they'd found a way to mine blocks easily, but unfortunately it only works on regtest and not on the mainnet where the blocks are actually worth money. The Bitcoin SV team actually uses the regtest option extensively. Every Bitcoin SV version, we run up hundreds, probably thousands of simulated Bitcoin networks to run various tests, etc. So it's something that we find very useful. On the Bitcoin CLI part, though, I believe that there are some services like What's on Chain and maybe MatterCloud that actually offer REST APIs that are basically the same as some of the RPC calls that you get. I don't think, I could be wrong, I don't think they offer them in the straight JSON RPC format. In fact, that's a service that we considered building a while back in nChain, but didn't get to it for whatever reason. Although there are any application developers out there right now that are looking for an idea, that actually could be something that's quite useful, because it's easy to download the Bitcoin clients, the Bitcoin software, the Bitcoin SV software, and run up a regtest node, because it doesn't require all of the mainnet block and transaction history. But of course, it's a much bigger task to download the entire blockchain and validate it. If someone was to offer a service in front of Bitcoin SV that exposed some of the RPC commands to people on a user by user basis, that would be potentially a very useful thing, because you could use Bitcoin CLI as a client to a remote service and gain access to all of those commands. So there's an idea for anybody who's looking for a way to whet their appetite for developing in the Bitcoin SV world. I've got one last question here. I'm not quite sure I've figured out what it means, which is from Maria. She's simply asking for more explanation of op push data, op drop.
Yeah, I mean, so that obviously one of the methods that we mentioned. Really, that's kind of, we often see a push data paired with an op drop statement, even though that's not, there are cases where you might put data in script for the function of the script. Using the push data op drop pattern is for when you want to push data into a script that isn't really necessarily relevant to the validation of the script. It's kind of just adding it as a component, and then by pushing it and then dropping it immediately, what you're doing is, again, pushing it to the stack, removing it from the stack. So it's kind of interpolating your data into whatever important validation part of the script there is. And again, that's quite different to what's post op return. When again we said we don't actually need to use the push data convention even, but it's still done quite commonly as a formatting thing.
Yeah, so it's effectively a no-op. If you have a script that's got push data and op drop right in the middle of it, it is functionally exactly the same as if the push data op drop wasn't there at all. So, Jack, would that be potentially one vector that miners could use to prune data into spendable output?
Yeah, I think so. I think this is one of those avenues where it's not necessarily what people have been doing yet, but obviously the node just needs to have enough information to validate the script in total. They need to check that the whole script validates to true. So yeah, if you have something that's effectively a no-op in the middle, then maybe that's something you don't necessarily need to store to do that check in the future.
Yep. Okay. Well, there you have it. If you want to ensure that it doesn't get pruned, then you'll have to come up with something funky like a hash puzzle that involves your data so that the miners can't prune it that easily. Having said that, I don't think we're seeing many signs of widespread pruning at this point. So, okay, I think we have a few more minutes before our next presentation. Not too many, I don't think. It's another N-chainer who's going to tell you a bit about the Light Client program and show you an early demo of some of the work that has been done to help put the tools in your hands to make the peer-to-peer SPV paradigm easier to realize. So we'll be back in just a moment, and we'll see what Jad has got to say. Peer-to-peer has been a long time coming in the Bitcoin world. It was first described by Satoshi Nakamoto in the white paper itself. And one of the few people in the history of Bitcoin that actually got it was Mike Hearn, the original author of the Bitcoin J library, which we actually still use internally in Nchain today. Over the last couple of years, the Bitcoin Association infrastructure team has been busy putting together a lot of the missing pieces of the puzzle, I suppose, to make true peer-to-peer interaction with Bitcoin possible. They're not necessarily the only way to achieve the outcomes that each sort of part solves for, but it is one set of tools. And these include things like Paymail, Mappy, Miner ID, SPV channels, and many more, including some enhancements on the Bitcoin node software itself. we've been working hard in the infrastructure team to try and make this more accessible and more usable. And to that end, in fact, recently put together what we call the Light Client program, which is not really something new. It's just recognizing that there are some incomplete parts to the puzzle. So the peer-to-peer story is not finished being written yet. There are parts of this, how users and merchants interact, how we resolve messaging problems and service discovery, etc., that are still, very much works in progress. The Technical Standards Committee will be heavily involved in this, and I expect, and in fact, I've already seen other people tackling some of these problems. So for an early access peek into what we are trying to do to smooth the road to peer-to-peer adoption, I would like to introduce Jad, who is lead of our rapid application development team, otherwise codenamed Bostave. I'll let him try to explain to you why. And he'll be showing us some of the early versions of SPV implementation.
Wahab, and this presentation is about scaling Bitcoin for global adoption. Now, I know there have been many presentations in the past with a similar title, but this presentation has a few things that have never been spoken about publicly yet. So the proper way to scale the Bitcoin blockchain for global adoption is to basically use the Lightning Network. No, it's not. No, it's not. So what I'm actually going to be talking about is SPV. So I'm going to start off giving an overview on Bitcoin scaling. Then I'm going to discuss simple payment verification, SPV, what it is, why it's important, and how exactly it can be used. And then I'm going to go through an end-to-end SPV flow, covering existing tools and highlighting missing tools and tools that need more work. So this is the Bitcoin network. It's represented by a mandala network, which consists of two main components, the highly connected center of nodes being the first, and the second, the rest of the users on the outside connecting in, as well as to each other peer-to-peer. Now, in order for us to scale Bitcoin, it's not enough to only scale the nodes or the miners, which are essentially the same thing. We need to also scale the users. So work on scaling Bitcoin, the user side pretty much started when we had a few mainnet stress tests and services like Money Button and others started falling over. And at that time, everyone was just running their own node like it was a normal thing. And but then everyone realized that we can't keep this up and we need to do things properly with SPV because users don't need to run a node and they shouldn't have to validate every single transaction on the planet. Instead of just caring about their own, they should just be worried about their own transactions and leave the rest up to the nodes. So this is another cliche Satoshi quote, but it's just to remind people that there really isn't anything new here. In the early days, even Satoshi in 2010 said that the current system where every user is a network node is not the intended configuration for large scale. That would be like, every Usenet user running their own NNTP server, and the design supports letting users just be users. So, we're not just doing things the way they were originally designed as some sort of PR stunt. We've studied other blockchains, other solutions. We've come to the conclusion that the original Bitcoin design is the best solution. And it still blows my mind that Bitcoin's original design is the best one out there, despite being the first, and not just because it was the first, as some people imply. So simple payment verification, SPV, it's basically section 8 of the white paper. Clearly states that it's possible to verify payments without running a full network node, and we'll see why in the next few slides. And the user only needs to keep the header chain, which is the copy of the block headers of the longest proof of work chain. And before I explain SPV and how it really works, does anyone want to guess how many proper SPV solutions there are after 12 years of Bitcoin's existence? There's zero proper SPV solutions, or else I wouldn't be sat here giving this presentation or writing the tooling for it, would I? So this is how the Bitcoin blockchain works. Basically, the word blockchain is a bit misleading. It should more accurately be called the block header chain, because the way it works is the Bitcoin block headers are chained together, and each block header is only 80 bytes that include the version, the previous block hash, which it builds upon, the Merkle root of the transactions, the timestamp, the difficulty target, and the nonce. So each header is only 80 bytes, regardless of how big the block is or how many transactions there are in the block. All transactions get put in a Merkle tree, and only the Merkle root is in the block header. And basically, there's a reason why there are Merkle trees in Bitcoin. As you can see in my extremely naive drawing, you can keep adding more transactions into the Merkle tree, and that won't affect the size of the headers. Basically, all you need to do is just keep a copy of the headers, and the nodes take care of the rest of the transactions. All you need to care about is having the header chain, and if you've got a transaction, as you can see here in yellow, all you need is the Merkle path in light blue to prove that the transaction actually existed in the block, and that's all you need to cryptographically prove that. So you don't need the whole block, all you need is the header chain. And if you had a limited size block of 1 megabyte, like on BTC, there would be no reason to have a Merkle tree. Basically, all you would do is just hash the transactions all together and put that in the block header. You're just adding unnecessary complexity by having a Merkle tree, since everyone on BTC runs a full node and there's no differentiation between nodes and users. That's why no one really uses SPV on BTC. So this would just, adding a Merkle tree is just adding extra unnecessary complexity. And technically, so I don't get called out on this, what you would do is you would actually hash the Coinbase separately from the rest of the transactions because of the extra nonce. But anyway, you get my point. So these are a couple of diagrams from my previous presentation I gave about MAPI. And for those of you who haven't seen it, MAPI is pretty much just an interface into nodes or miners. But if you want to understand MAPI in more detail, you should check out my previous presentation. But pretty much in these diagrams, I compare a legacy to peer-to-peer payments. And I just wanted to clarify a few things. So the way legacy payments used to work on Bitcoin is the sender would send transaction to the network, and then the receiver would scan all the transactions on the network and filter out for the transaction that they're interested in. And I just wanted to say that it's not technically not unscalable, it's just over expensive, because you could have someone send you a payment to the network and have a service provider scan the network and send you the transaction that you're interested in. So it's still doable, but it's just over expensive. It's like buying a private jet to send a letter from London to New York. No one's going to do that, but no one's actually stopping you from doing that if you had the money and you really want to do that. So also to clarify one more thing on the peer-to-peer payments diagram. So there's actually one thing missing. So it's having the receiver broadcast the transaction is one step further, but it's still missing something. So the way peer-to-peer payments work is you hand the receiver the transaction, and the same way you would hand a check to someone, they would cash it at the bank. You hand the transaction to the receiver, and they would settle that on the blockchain. So the difference here that was missing in the previous presentation is that the merchant or the receiver would validate the transaction, and then if it's invalid, they would reject it. If not, they would settle that on the blockchain and broadcast it to the nodes. So how does transaction validation work? First of all, you need to make sure that the sum of the input Satoshis is greater than or equal to the sum of the output Satoshis, or else you'd be essentially creating money out of thin air. You also need to validate that the unlocking script, previously known as the script sig, in the input can unlock the locking script, previously known as the script pub key, in the output UTXO being spent. So, and basically this is an example transaction. And with the input here, as you can see, it's got transaction ID of the UTXO, the index, and the unlocking script and the sequence number. But if you notice something, if you look at the output that it's spending, there are a couple of things missing. There are two main fields missing. So there's the value Satoshis that's missing and the locking script that's missing. And in order to validate the transaction, you need that data from somewhere because it's not in the payment transaction itself. And we'll cover that in more detail later on. But basically, once you validate the transaction, you need to send it to a node in order to check if the UTXOs are unspent, meaning that there's no double spend involved. And basically, we trust the competitive nature of the miners and the nodes, and that's why this is secure. Because you can't get a double spend into the blockchain, or else your block is going to get orphaned by the rest of the nodes. So I know people are thinking this because it's a common question that people have about the situation. What's the point? So you may not be convinced and maybe thinking, why should the merchant receiver even validate the transaction? The node or the miner will do it anyway. So what's the point? So it's not. So it's not because of any theoretical reasons. There are real practical implications for not validating the transaction before broadcasting it. So first of all, for example, how would you check how much fees a transaction is paying? So let's say a sender sends you a transaction not paying enough fees that you would like, and then you send it to the miners, and then it gets accepted by the network. It's too late. You can't update it. There's no replace by fee. So that's a huge drawback of not validating the transaction yourself. Another one is state channels. So how would you validate an interim state of the state channel before broadcasting it to the network? So you need to validate the transaction yourself. Also, if you have multiple inputs, are you going to wait until all of the inputs are signed and received before validating the transaction? I mean, we're not going to have only transactions with one pay the public key hash input and two pay the public key hash outputs, one for change, forever. Things are going to get much more complex. Multi-sig, spending multi-sig outputs as well. You want to validate that in interim states without having all of the signatures yet. Also spending complex scripts, which potentially could be very expensive in the future. So you want to know that before broadcasting and potentially reject that transaction from a sender. Also, if you're just sending invalid transactions to the network, nodes could get banned. Obviously, that's something you don't want. Error messages is a big one as well. So the node doesn't return the best error messages always. And if you've been programming Bitcoin, you probably know that already. For example, missing inputs, it's not the best error example. So if you validate a transaction yourself, you could know exactly what's wrong. And basically, yeah, these are just a few practical implications. I'm sure you guys can think of a lot more, but validating transactions before accepting them actually relates a bit to the up push transaction technique that a lot of people in the industry are using now. So I'd like to just quickly go over that a little bit. But before I explain up push transaction, let's just go through quickly how spending a UTXO works in Bitcoin. So you have a transaction here, a UTXO, pay the public key hash UTXO, and you want to spend that. And then another transaction, basically you need to include a signature and a public key in the locking script. And what the signature is signing is this sig hash pre-image, which includes these fields, and a lot of them, for example, the version, the unlock time, a lot of them are outside of the script itself. So the way up push transaction works is, usually nothing should be able to access any data outside of the script, but up check sig can, and this is what up push transaction takes advantage of. And that's why we called it a Ying's hack back at Nchain, before it was called up push transaction. because it takes advantage of something that in a hacky way, basically, that wasn't intended. That wasn't its intended purpose. So the way up push transaction works is basically you push the sig hash pre-image in the unlocking script with a random private key, and then in the locking script you ECDSA sign that sig hash pre-image and then use op check sig. If the check sig passes, then you know that you have the same sig hash pre-image as the current transaction and can use values in there like the previous transaction script or the unlock time, etc. So in the locking script, you would include extra logic. You could force the output script to be a specific output, and people are using that to force an output of a transaction spending a specific input to be exactly the same as the previous output script of the input, basically carrying forward the script, sort of like a Ethereum smart contract. You could also force the output value to be a specific amount. You could force the unlock time to be a specific amount, but there's, for example, with op CLTV, the reason why we got rid of it is there's no real need for it. There's cheaper and better ways to do it. And when validating a transaction with SPV, you can check the outputs and whatever logic that you want and reject if the transaction doesn't follow the specific logic rules, the same way you would do with op push transaction. But the difference is these rules don't need to be in the transaction script and enforced, enforced by the miners. Anyway, that's enough about op push transaction for now. I don't want to take anything away from Xiaowei's presentation tomorrow. I really like his work, and I'm sure his presentation will be great. What I want people to take away from this is to think carefully about what their solution is trying to really achieve and not just jump to conclusions. There are no silver bullets, and op push transaction is not cheap. So we've gone through why scaling Bitcoin with SPV is important. Now let's talk about how to go about doing that exactly. So this is a diagram of the SPV flow end to end, and it's pretty similar to MyCurrent or BitPay's payment protocol setup, but more advanced and with less complexity involved. So I know this looks a bit overwhelming at first glance, so I'm going to go through it step by step, don't worry. And before going through the flow diagram, I just wanted to give you a taste of how the UX looks like so that it would be easier to understand the flow diagram. So this is an example video of a hand cash wallet buying something at a store using AnyPay. So what they would do is take their hand cash wallet, scan the QR code of a specific item that they want to purchase, which is essentially the purchase order, and then their wallet would basically get the information for that transaction, and then you would swipe to accept the transaction, essentially signing and sending the payment to the merchant. So I'm going to go through the diagram and highlight specific parts that need work and more discussion, and I'll discuss them afterwards separately in different slides. So in the beginning, the customer wants to buy something from the merchant. They create the basket of goods, which is essentially the purchase order, as you saw in the hand cash example. And the merchant would create the invoice with X amount of Satoshis, and then display the invoice as a QR code. So let me just break that down a little bit. So this constitutes the payment protocol initiation. The first part is essentially service discovery. So you need to discover the merchant, and some solutions such as Paymail do that service discovery, but something missing with Paymail is invoice creation, and we'll discuss that a bit more in the later slides. So basically the way this works with the payment protocol that Handcash and AnyPay use is once the merchant creates the invoice, they basically create an invoice ID for that item locally in their on their servers, and then they display either a link with this URI, or they encode that into a QR code which the wallet scans, and that's where they obtain the payment protocol URL, and that's how they know where to fetch the payment request with the invoice ID. So after that, the customer's wallet fetches the payment request, and then from the merchant at this endpoint, and then the merchant would get a policy quote from the a node using MAPI. And what a policy quote is essentially it's just an extension to the fee quote with other minor policies such as the ancestor limit and stuff like that, which is being added to MAPI. And once the merchant gets the policy quote response, they can work out the payment request arguments, for example, the outputs that they want to receive, the payments to, the fees, etc. So this is how a payment request looks currently. As you can notice, the fees are not included, which we'll discuss in the next slides as well. And then the merchant would respond to the customer's wallet with this payment request. At that point, the customer needs to authorize the payment, which is where you saw the user swipe to accept the payment, click OK, and then that's where the payment is sent to the merchant. So one thing missing from the current implementation is all of the metadata or extra data needed to validate the transaction, which we're denoting as the SPV envelope. So this consists of the input transactions, the Merkle proofs, and we'll explain that in the next slides as well. And that's also missing from the current implementation. And then once the merchant receives the payment transaction, they also need to validate it. And at the moment, it's not being validated using the right approaches. So we'll discuss that later as well. Once the merchant validates the payment transaction, if there's an error, it would immediately reject it, and then that ends it right there. Or they would then broadcast a transaction, so post it to a MAPI endpoint, including their callback URL, so that they can immediately be notified for any double spend notifications, double spend attempts, and afterwards, when the transaction is mined into a block, they can get the Merkle proof for it. So if they get a success response from the miner, they would then respond to the customer with a payment acknowledgement. And then afterwards, this is something that doesn't exist yet, but obviously the customer needs the Merkle proof of the transaction as well, because likely they will have a change output and they will need the Merkle proof for that as well. So there needs to be an extension for the MAPI in order for someone who's not submitting the transaction to get the Merkle proof of a specific transaction. Maybe they can resubmit or query transaction, but there needs to be an addition to MAPI for them to also get a Merkle proof. And one more thing to mention is how would the merchant or the customer discover the right MAPI endpoints, and we'll discuss that in the next slides as well. So the first thing I wanted to discuss is invoice creation. So it's currently missing with Paymail. With Paymail right now, if you want to send money to someone's Paymail address, for example, jad@moneybutton.com, you just send money to that address, you set the amount, it's not linked to any invoice or anything. And that was basically to mirror existing Bitcoin user experience where you send money to someone's address unsolicited, which is a really rare case. You're never going to be paying for someone unsolicited without, them having an invoice or anything, paying them and them requesting the payment. So this, I would say, in the future, it's gonna get even more rare, especially when all these new tools start being used more often. So similar to the payment request, we have a payment capability, which is the payment destination, and similar to the payment in the payment protocol, we have the P2P transactions paymail capability. And the difference here is it's not linked to any invoice or anything. All you do is you request payment destination for a specific amount of Satoshis, you get a reference, and then you quote that reference when you're submitting the transaction. So it's not as good as a payment request or the payment protocol, which people call BIP 270. But anyway, it needs some work. So the second thing I wanted to discuss is the fees in the payment request, which are currently don't exist. So we need to extend the payment request in the payment protocol spec to include the amount of fees. So right now the merchant or the receiver gets the fees from MAPI, and they get the fees from different miners, and they need to decide which fee that they would set for the payment for them to accept that payment. So we need some work on this, and I'm sure this is something that a lot of people, a lot of wallets and stuff in the space will definitely benefit from. So we need to standardize this across different wallets so that we can get proper interoperability. The third thing I want to discuss is the SPV envelope. And this is in order to send the right data in order for the receiver to validate the transaction properly. So some wallets get the previous transaction data from an external service like what's on chain, but that's not the best solution. It's just a hack at best. And the sender should send you all the information you need to validate the transaction. So what an SPV envelope is essentially it's a data structure encapsulating this information, this metadata that you need to validate the transaction, basically the payment transaction itself, or could be multiple transactions, the transactions that correspond to each input, as well as their Merkle proofs. And the sender will basically already have much of that information because they need the previous transaction info when signing the input. And there's currently a TSC work in progress getting started. So if this affects you or your company, please get involved and actively work on getting the right standard across different wallets. And the fourth thing which relates to that is validating the payment transaction. So I conveniently stole this great diagram from my colleague Jack. Basically shows the elements that I just discussed: the payment transaction, the input transactions, the Merkle proofs. And then, so once handed the payment transaction with the SPV envelope, you can go through the following steps to validate the transaction. For each input, you need to verify the Merkle proof, and there's an asterisk there because you need to validate the Merkle proof across the longest chain. So you need a headers client to essentially find the longest, most proof of work chain. And we have an internal headers client that will be released soon. And then second of all, you need to validate the unlocking script and check the fees paid or any other rules or logic similar to the outpush transaction technique. And then finally, you accept and broadcast the transaction to a node. The fifth thing I wanted to highlight is the Merkle proofs. So at the moment, the Merkle proofs have been standardized with the TSC, and it's in public review stages, so it should be finalized very soon. And MAPI version 1.3.0 uses the latest Merkle proof standard, as well as Bitcoin SV node version 108. And the last thing I wanted to highlight is MAPI. So how would you write code to discover MAPI endpoints dynamically? I know most of the MAPI client libraries right now hard code a lot of the node details into the code, which is not great. The Bitcoin design supports nodes joining and leaving dynamically. So why shouldn't our code? So some steps have been taken already to solve this. Bitcoin peer-to-peer messages have been extended in order for them to return the Coinbase transaction as well as the Merkle proof, along with new block headers. And once you have a headers client, basically you can extract the miner ID data from the Coinbase transactions of each block, and then you can find the data of the specific miners. Right now, it's just Tal, Mempool, and MatterCloud that are doing that, but as the blockchain scales and grows, I'm sure it's not going to be them three. So miner ID is going to be crucial for that, not to mention all of the other reasons why miner ID is important for scaling for miners directly. So once all of these 6 actions have been completed, we should have a fully complete SPV solution, taking us one step further towards scaling Bitcoin for global adoption. Now, myself, along with a bunch of others, including some Nchain, Tal, and Tonic Power, building a lot of these foundational tools and building blocks, open source in Golang. So for more information, go to gobitcoinsv.com. You'll find a collection of a lot of Golang Bitcoin repositories. And we've been also building extensive Bitcoin libraries under the GitHub libsv that started off based on Ryan and Muddy Button's JavaScript library. And then we just went for a ground up approach, removing all legacy BTC, BCH baggage. So it's just purely Bitcoin now. Right. If you found this presentation interesting and relevant to what you're currently working on, please reach out and get involved so that we can design the right standards for interoperability without missing anything or anyone. So you can reach out to me using any of the following methods. The sooner we can sort out scaling the Bitcoin users aspect, the better for everyone, and the faster we can move on to other things. Thank you.
Thanks, Chad. You seem to have struck a chord there because we've solicited quite a few questions. There seems to be an interesting, odd theme in the names of the people asking the questions. I don't know if this is a person or a few people having a bit of a laugh, but I'm guessing that there's an Aussie in the audience. Anyway, so the first question is, when will the first proper SPV client be released, and why has it taken so long?
Yeah, so basically, as I mentioned at the end of the presentation, there's like 6 more missing pieces until we have a proper SPV client. And the main reason why it's taken so long is because it's not really something people can make money off of. You can't really sell an SPV client. It's like an open source library that anyone could run. So pretty much people have just been building their own bespoke solutions. And another reason is because, you know, BTC has like crippled Bitcoin for so long. So no one really needed SPV on BTC with small blocks. So it's, yeah, it's never been needed.
Yeah, that's true. And also, I think some of the server-side services that were actually required for wallets to be able to do this either were missing or implemented quite badly. I think I said in the intro, Mike Hearn was one of the first people who ever really got SPV, and he implemented Bitcoin J, which did parts of SPV, but being able to actually get Merkle proofs back from miners and things like that were made a lot more difficult by the network model that BTC adopted, where there were thousands and thousands of nodes and you had no idea which ones were actually the miners. So yeah, it's a large task to make the server-side services available, which has to be done before wallets can even begin to start implementing. But we're getting pretty close now. Our next question was, how can we be sure our SPV wallet is connecting to the legitimate header chain?
Yeah, so that's basically the way proof of work works. So the way you validate the legitimate header chain is it's basically the longest proof of work chain, and you can easily validate that objectively by calculating the hash yourself. It's extremely fast and extremely reliable cryptographically. You just compute the hash and you check that it's less than a specific difficulty. And that's actually a big criticism of proof of stake. So there's no way to objectively verify that a block header is valid on like proof of stake, because the miners don't really do any hashing that you could verify objectively. They basically just stake their coins, and you need to validate their signatures. So you need to know who the validators are at any specific point in time. And it's just, it's not really secure. And the way they solve it is essentially by adding checkpoints. So with proof of work, anyone could just validate that the chain of block headers is the longest by just calculating the difficulty on that.
That's right. So the goal is you would actually try to get all of the headers out there, even ones from other chains, so that you can calculate for yourself which is the longest. Yeah. So how does the receiver of an SPV transaction eventually get their Merkle proof? That's a very good question.
Mm-hmm. So basically, there's been an extension to MAPI version 1.2 and above, that once you submit a transaction to a miner, you provide your callback URL, and then once the transaction has been mined into a block, you would get a callback with the Merkle proof of the block it's been mined in. You could get multiple, because a transaction could be mined in multiple if there's a temporary fork, which is a normal part of the way a Bitcoin Nakamoto consensus works. So that's pretty much how you would get the Merkle proof. A lot of people right now, since they've been building their own bespoke solutions, different wallets do different things. They can, get stuff from what's on chain or service providers like Mattercloud and that kind of thing. So the MAPI way of doing it is much more straightforward and much easier. And there's been the TSC standard that's sort of standardized the way Merkle proofs are displayed in JSON and binary. So that makes things a lot more easy to write code for.
Sure. And I guess the difference with MAPI is that you're actually able to have a direct conversation with a miner and get a response from them, rather than having to wait potentially minutes, maybe even longer, to see what might actually happen as a result of your transaction being broadcast. So we've got a question here from Angus. What prevents a merchant from claiming that a payment hasn't gone through, when in fact, presumably it has?
Question.
We might have lost Jad.
Basically, go through
Jad, I think we might have lost you there.
Hey, do
You might have
hear
a
me
bad
now?
connection. Yes, that's better.
Yeah. That's better? Yeah, what was the last thing I said?
We didn't really get to the start of the answer. I think you cut out before you started.
All right. Okay, so the answer is, for example, let's say the transaction is not paying enough transaction fees. So that would prevent a merchant from accepting the transaction. Maybe they want it to be mined in the next block, so they would need a specific amount of fees. Maybe they're satisfied with not having it mined in the next block because it's like like Amazon, it's going to be shipped in 5 days, so it doesn't need to be cleared on the blockchain network immediately. So they're fine with accepting lower fees for it to get mined within the next day, or it's probably going to be within the next hours or something, since blocks get mined every 10 minutes. So that's something that would prevent a merchant from accepting a transaction. So they can have all types of rules as well.
Yeah. And from the client side, I think knowing that the merchant is going to receive a signed response from a miner who has reputation, I think the client would probably be able to know something was up if they didn't actually get such a response passed back from the merchant. Because for the merchant to claim that the miner had rejected it, they would essentially have to forge a signature from the miner as well.
Just
our next
one
question.
thing to add as well, sorry to cut you there, Steve. But this also relates to the up-push transaction stuff. So basically what up-push transaction does is it forces a transaction to be a specific way, or else it won't be able to get mined on the blockchain. And the same way, once you receive a transaction, you could verify it yourself. And if it's not, for example, the script is not the same as the input script, which is what a lot of up-push transactions do, you could reject it from the sender. And that's a much cheaper way of doing it, and having miners validate that. You could validate that directly and reject it.
Yep, that's right. Can you think of any examples of think of any SPV examples that are not appropriate under the invoice paradigm, i.e. BIP 270?
Yeah, so this is if you're doing stuff like Twetch. It's like an open protocol, for example, where a lot of different people are putting data on the blockchain, and then you want to collate all of that data and use that from different people. So that could be done in some sort of BIP 270 payment protocol way, where you submit it to a server that only collects that type of transaction, or you could have a listening node that listens on the blockchain for specific transactions in that way. So if you're just putting data or stuff like that, but I would say pretty much most transactions can and will be done much cheaper using the payment protocol, because you don't have to know about all the transactions on the network. A transaction is going to be known by the sender and the receiver, and maybe a few other third parties, but not the entire network.
That's right.
So that's where the P2P stuff comes from.
I think it's probably important to point out that BIP 270 is a peer-to-peer interaction, but it's not actually SPV itself. SPV is about proving that a transaction has some connection to, or is connected to the blockchain and has been included. A transaction that has not yet been submitted to a miner, or may have been submitted but not mined into a block, doesn't have an SPV proof. So whilst it's a vital part of this whole workflow, it's worth being careful about what you sort of call SPV and what is actually another part of the peer-to-peer interaction. So last question before we get to the interesting one. Not that they're all not interesting. This is from a merchant. Will miners start charging SPV clients for getting block headers from them? I'll preface this by saying I'm actually planning on asking Craig some questions about how header distribution will work.
Yeah. So if you remember what I said about the block headers being only 80 bytes. So that's pretty much only 80 bytes every 10 minutes. And that's like minuscule, like tiny. A picture of a cat on WhatsApp is, orders of magnitude greater than that. And you get hundreds of pictures on WhatsApp and stuff like that. So I would not think it's not going to be charged for any time soon, if ever. And basically the distribution network on Bitcoin, you don't have to get them from miners. SPV clients can distribute them to other SPV clients as well. So it's really, really lightweight thing. And in the future, the header chain is sort of going to be like the heartbeat of the global blockchain, and it's going to be extremely straightforward. It's not going to be like something that's hard to get. It's going to be pretty much everywhere. And even in the white paper, Satoshi planned that this is going to be anywhere. Like the blockchain, the header chain grows in a few megabytes per year, and it's really tiny. So I don't see it being a problem anytime.
Yeah, that's right. No, I mean, even if miners did want to charge for it, fundamentally they only really need to send it out to one party, and then you can use peer-to-peer exchange to distribute them. The last question is an interesting one. I'm not sure whether I should take this or throw this one to you. It's who is Ying? You mentioned the mysterious Ying a few times in your presentation.
Yeah, sure. Ying is a researcher at Nguyen, and back in like 2016 or 17. He designed the push transaction technique, which was basically before the hackathon for the tokens that the tokenized team won, and that was a way of basically pushing the transaction and overloading the checksig opcode in order to get data from the transaction, which isn't usually the case.
Yeah. So Ying is a very smart cookie and is still working very closely with Nchain. Probably has a deeper understanding of the push-TX technique than maybe anyone on the planet. So yeah, we were very glad to have had Ying as part of our research team. That's the end of the questions. No, there is one more. Something like Mina protocol, M-I-N-A. I'm not actually sure what that means. Does that ring a bell to you, Jad?
Never seen it, no.
No, okay. We might have to take that one on notice. Okay, well, yeah, SPV is an incredibly important subject, and I wanted to emphasize it because I expect that we may have some people who are considering or building an application on Bitcoin here in the audience, or maybe some people who have started, but they're not that far down the road. really consider carefully the role that SPV will play in the architecture of your application, because if you're using Bitcoin SV software as part of your tech stack, you will inevitably run into a problem down the track as Bitcoin scales. It's in your interests to start thinking about adopting the SPV paradigm very early on in the architecture stage of building your application or service. So we'll be talking a little bit more about some of those features tomorrow, but I will do a bit more of a description of what's coming up tomorrow after our next segment. So we'll take a short break. In a few minutes, I'm going to be back for a fireside chat with the guy who it all began with, Dr. Craig Wright. And hello to Craig. Welcome to our second DevCon fireside chat with a virtual fire. We'll have to use our imaginations. Welcome to DevCon, Craig.
Welcome. How are you?
I'm good. Talking to you from Zug in Switzerland today, rather than on the chair next to you. But geographic restrictions are something we're going to talk about today, and how Bitcoin helps us overcome them. So I want to focus on some technical and economic aspects of Bitcoin. And last time I asked you a few questions about a few design decisions that were made in Bitcoin and why they were there, and we dug a bit deeper into what some of them actually meant.
I'd like to continue that theme with a few points from the white paper. I'm still 10 years later finding new things in the white paper and understanding things a bit differently to the way I did the other 100 times that I read it. But I want to actually start with a question of grammar, actually. It's a question that I've been asked quite a few times, which is there's a data structure in Bitcoin called the Merkle tree and another smaller version of it called the Merkle branch, and then there's the Merkle proof. It's named after a cryptographer, I believe, by the name of Ralph Merkle, which would imply that it is meant to be capitalized. And this has been a question of much debate over the last year for me in particular. So I'd like to throw it to you for the definitive answer.
Okay, so yes, you should capitalize it as a name. And if we want to go into the full sort of grammatical correctness, because it's referencing a name, we should have single quotes around it. But that's pulling out the old predicate logic type naming rules for syntactic logic. But if we're doing the grammar correctly, it should be a capitalized Merkle. And if you want to show off and be totally wanky, you can put single quotes around Merkle, like no one ever does anymore, because no one has learnt this stuff in, well, since the 50s, apart from me. Well, and I'm sure people will argue that I've been around that long, but I haven't.
If we're going to enforce that, I have a lot of documents that I need to update, and it sounds like a job for grep rather than a manual task.
But then again, you're also in information technology, so no one expects you to even know how to use a comma.
I saw an interesting comment on Twitter the other day, which was about the obviously posted by an Australian commenting on the updated Bitcoin documentation, starting to use the Z form of words like decentralized or centralized, this or that. And they called it the decentrification of Bitcoin documentation, which is something.
Yes, the de-Englishification, yep.
Yes. Okay, so let's move on to Bitcoin design decisions. Again, in preparing for this, I had another detailed look through the Bitcoin white paper and picked out a few things that have stood out to me over the last few months. It won't surprise anybody to know that I probably look at the white paper at least a few times every week to clarify certain things. And first, we'll focus on section 5, which to me is one of the standout parts of the white paper, because it defines what the Bitcoin network actually is, as well as defining what a node is. And one of the steps in running a network says, and I quote, "When a node finds a proof of work, it broadcasts the block to all nodes."
Yes.
Now, it was only a few months ago that I noticed that word "all" in there, but I think it actually has some pretty profound implications. Does this imply that nodes not only should be connected to all other nodes, but that they're not responsible for relaying other nodes' blocks?
So what we're meant to do is actually ensure that the network is a small world network. It should be a near complete connection. So we're not going to go into graph isomorphisms or any silly mathematical stuff like this, but if you don't have a complete graph, it's still okay. I mean, you should forward if it's there to forward, but it should connect to practically everyone. So the process is you receive a block, and then you just do a quick check. Anyone you're connected to, do you have this block? If they don't, then they should be able to go, yep, I want it. And you should then send it. And not everyone should send everything everywhere, because why receive the same block 50 times? Remember, if you have the block header, you have from one node, you have sort of everything to prove the block everywhere else. So once you have the block header, you can prove it. I mean, so yes, I want to check the block header multiple times, but I don't want to check the whole block multiple times.
Yeah. So a well-connected Bitcoin node would be taking responsibility primarily for getting it to all of the other nodes, wouldn't it? Because it's in its interests to do so.
Correct. If you are sending your node out when you've discovered one, you want to get it to as many nodes as possible, as quickly as possible.
When you're receiving a block header from another node, is it as in a block that you haven't mined, some other node has mined it? Is it interesting to you to know how many other nodes have seen that block and how fast they've seen it?
Yes, it very much is. This allows you to work out the connectivity and where you should aim sending first. Now, there are different methodologies in sending on networks. Although it says send everywhere, you could blap it out to everything equally. Now, that could be a problem in that some slow networks may actually degrade you getting it to large networks. So nodes will start working out that this guy has 30% of the network. This guy has 10%. This guy has 2%, but he's really fast. This guy has 5%, but he's on a terribly slow dial-up modem. And they will start working out how best to send around the network. So optimizing the network traffic will occur, but that's only going to occur if you can start working out, well, what connectivity this guy has. Are they responsive? Do they forward? All sorts of things like this.
Okay, so if you're looking for the fastest path to get your block accepted by a majority of the network?
Correct. You want to get it to everyone, but what you want to do is, I want to get it to this 60%, then I want to get it to that 30%, then that 10%. That's only one example. Maybe it's that 30%, then that 30%, etc. But you're going to work out for your particular set of connectivity, your particular set of network computation power, what is the optimal methodology for my company to send everything around the network, and it's going to vary. That's part of what I'm actually doing with my PhD at Exeter at the moment. I'm trying to work out, decompose the graph from the node point of view, so that they can create a formula to say this is how we should be connected. We need extra bandwidth to China. We need extra bandwidth to the US. Japan's fine. UK's fine. That sort of thing.
Yeah. Okay. Well, that's interesting because we're actually the Bitcoin SV team is currently working on introducing the concept of connection priority, so that when you have a block to broadcast, you can actually choose which nodes to focus your resources on first. And we had planned that primarily so that people could draw a distinction between Bitcoin nodes on the network, the ones that are actually producing blocks,
and merchants and home users,
other people that are connected who are essentially sort of draining your resources. There's no reason for us to use our resources sending them blocks when we actually should be sending them to nodes first. But it sounds like there's
it will even stop DDoS attacks, because if you just stop connectivity between all of these random nothings, whenever someone does an attack, then you're still able to process all your connections. You still want to have a methodology for getting transactions in, of course, otherwise you're not going to be able to earn anything. But equally, you want to be able to sort of make sure that the majority of other nodes see your block as quickly as possible, so that they don't go off and discover another block that competes with yours.
Yep. So we had a discussion a little while ago about terminology again, and we're talking about people who are connected to you who aren't actually nodes. Now, they may well still be running the Bitcoin SV software, but they don't fulfill the definition of a node because they're not trying to produce blocks, or they're not producing blocks rather. And for a while I'd been calling them blockchain listeners, but after that conversation, I think you and I settled on the term blockchain block subscribers rather. Do you recall the rationale behind that?
Yeah, I don't mind using block subscribers because they're effectively not sitting there like people seem to think in a mesh promoting this block going around the network. What they're doing is basically sitting there and pulling information off the network. So it's a subscriber model.
Would you envisage that ever becoming a paid for model, a paid for service?
Some yes, some no. What I see is there'll be a variety of different models. So where I've said about overlaid networks, there'll be different connectivity requirements for things like exchanges, real ones one day, banks, other merchant organization that need really fast access. I mean, potentially the Amazons of the world will eventually hook in, the MasterCards will hook in, and they won't actually be nodes. Potentially they will pay some nodes for better access. I mean, right now, you get people in exchanges paying for dark fiber connectivity into the Australian Stock Exchange or Securities Exchange. Now I keep calling it the wrong name. I know they've remarketed themselves like a decade ago, but old habits. I'll stop one day.
I'm starting to lose track. I've been away from Australia long enough now that name changes I don't remember. Would you ever envisage this sort of cloud of block subscribers ever being serviced by a nodes adopting, some other technology, like stuff a copy of the block in BitTorrent and you can all figure it out from there and get it yourselves?
Well, if you've got the block headers, you can work out whether a block's correct. So any way that's quick. So there's no reason why not. I mean, why have Dropbox or Google Store? Why does Google run a pile of hosted cloud servers? Why does Amazon do the same thing? It adds efficiency. So economic efficiency is good.
Yeah. I can certainly imagine S3 being used and abused for some distribution on the network at some point. So let's turn our attention to some more definitions and probably one of the most important words in Bitcoin, the definition of a node. Section 5 of the white paper, I believe, is the canonical description of what it is.
Yep, it should be nice and simple, but it doesn't seem to be. Some of the simplest things always seem to be the longest and most horrible things for people to understand.
I know there are a lot of people who are actually clamoring for some clarity on this because the functions described in section 5, many of those functions are actually, well, I guess in the mining pool model, which is quite common nowadays, it's actually multiple actors that collectively perform all of those functions. So, I mean, the obvious example right now is a mining pool, which is what typically runs the Bitcoin SV software and builds the block templates, which then distributes them out to people who run warehouses full of ASIC units and do the hashing work rather. So where does the boundary of the node begin and end, and what should we call the other actors that are involved in it?
Well, the boundary is a difficult word. I mean, but if you have a group of sort of different entities who outsource part of their work, they're still going to be an entity. So the primary aspect of this is not, do I get proof of work and outsource it? Because those guys aren't really nodes. The guys finding hash solutions are just finding hash solutions. There's no difference to if they're doing it on rainbow tables. They're just checking very quickly a lot of rainbow tables. So it has to be the person who is the active mind, the coordinator. So who is actually deciding which transactions go where, which order, and how the block is constructed? They're the ones who actually set the rules and set who gets paid. If you think about it, they make the rules on who gets paid. They make the rules on the mining pool getting paid, any network providers getting paid. So he who has the gold, golden rule.
Yep.
Yep.
The very first nodes on the network were actually making use of outsourced services. For example, an ISP had to carry the transaction traffic from one node to another. And this isn't really any different in that sense, in your opinion, is it?
No, not at all. So, I mean, between Telstra and TPG and a few other ISPs, I had I didn't run my own, and even if I did, then there'd be a backbone connectivity point. It wasn't dark fiber around the world to everyone who wanted to connect. So
it almost sounds like it's more of a legal question than a strictly technical definition.
Yeah, I mean, where do you draw the line otherwise? I mean, I didn't have my own solar power. I had electricity lines that 90% of the time worked properly, apart from a horrible backup generator occasionally, but was stinky and noisy. So tried to get the power working properly.
We've got another section of questions on just that topic, actually, some alternative ways coming up. So I'm going to go out on a limb here and say, out of section 5, there are 6 steps. Step 2, each node collects new transactions into a block, which implies also that it's validating those transactions. This is probably the heart of it. This is what the actor that is performing step 2 is the one that you would probably define as the node.
Well, if you've got someone collecting transactions, then they're also choosing who gets paid. So they're going to choose. Think about it. If you do that and you're outsourced, you could chuck in your own transactions that for the mining reward.
Yeah.
I mean, where's that go? So.
Okay.
I mean, contractually, yes, you could sue people, but it's never good to give people the opportunity to get themselves sued.
So we've been talking in terms of nodes here. The other common term that is used to refer to these particular actors is miners. Where is that term appropriate? Is it the node operator? Is it the hashes? Is it something else?
That's going to vary. I mean, at the end of the day, the sort of controlling mind, the point that decides how the block's constructed, what transactions get in, what size the block they're going to work on, whether they stop at 1 gig or 10 gig, whether they want to reject anything that's not Catholic, like certain people in Bitcoin's history. All of that is really the sort of controlling body of a particular node. Like any organization, you can form partnerships and you can form corporations and trusts, and you can form businesses, joint ventures, all of these different aspects together in how you sort of distribute that over time. None of that existed in the early days of Bitcoin. So until 2011, well, end of 2010, people started playing with mining pools, but really 2011 on. Then it was just you ran a node and it was a little home user experience or a small company in one area. But after 2010, after 2011 on, we got to the point where people started creating alternative structures that they could run business as, which I hoped would do a bit more commercialization, and I didn't quite think of the hijacking. that occurred. But I mean, the irony there is everyone's looking at distributed developer groups and saying, like you were talking about with governance. Few people seem to actually know or want to know anymore that the Bitcoin Foundation was actually first registered before Satoshi left.
I didn't know that.
No, it was actually registered in 2010. That's why Satoshi is actually a life member.
I see. Does Bitcoin Foundation still exist as an incorporated entity?
Sort of. The only way to put it is, quite frankly, a shit show. The whole concept was it was meant to be a steward to govern the protocol, not but
as in it was supposed to play a role in the block size debate and in result.
Oh, there shouldn't have even been a block size debate. I mean, that was the whole point. There should never have been a block size debate. It should have just happened. It was just a limit that nodes could change whenever they want. And instead, a group of developers started this whole, the community rules, which, I'm sorry, how does the community give you any feedback? Other than Van der Waals and Voorhees and a few of the early guys sat there and went, the community has told me I've got my community consensus now. They want to do exactly what I want to do. It's amazing how the community always does what I want.
Governance by developer decree.
Oh no, it's not a decree. It's like when there's a papal bull. I mean, it's the word of God tells them, or something. I mean, it just comes down from all high, and they just know the will of the people.
Yeah, well,
it's like democracy in Soviet Russia. You can vote however you want as long as you vote Stalin.
Well, Bitcoin governance was actually one of the topics I was going to get to, so I might jump forward to that since we've already opened the hornet's nest there. When we came up with the Genesis spec, you were actually part of this process in terms of reviewing the terminology, etc. We defined, I guess, 3 categories of things that the software itself, the Bitcoin SV software, enforced using code. Now, enforced using code doesn't imply that is actually the rule. It's just you can code. You can build code to try to express any set of rules. And we divided it into 3 categories. There was the Bitcoin rules, there were the consensus limits, and then there were the local policies. Now, the Bitcoin rules is what we defined as things that were meant to be immutable and never change. They're just, that's the definition of the Bitcoin protocol. The consensus limits were things that probably should change, but they required some agreement from miners to emerge in some sense. And that's things like the block size limit, the consensus, the maximum amount of memory that can be used by the stack when a script is executing. Things that basically, if there were no limits, would enable anybody to reasonably trivially force a node to crash. So they're designed to expand. And then, of course, there's local policies, which are individual to a specific node. Anyone can change them anytime they want. There might be some consequences or risks to doing that, but they're essentially there for miners to have their own individual control without having to deal with consensus. So are you still okay with those 3 categories? And is there anything you add?
Yeah, I don't mind doing it that way. I mean, where people sort of miss some of this is there's a difference between changing the protocol where suddenly it doesn't work without changing the software. If you have to go around and make everyone upgrade and change their SPV client, then that's a no-no. If SPV keeps working, then that's your first test. Now, the other side where people got it wrong with like 1 meg cap and that sort of test, it should have never really been the test that they made it, is it's a unilateral contract. So if I put a sign up saying, I've lost 3 dogs, if you bring back my dogs, I'll pay you $100 each, then I can't force someone who's found 2 of my dogs to go out there and look for the 3rd one. They can go, bugger this, I've got 2 of your dogs, and you find the 3rd one yourself. The same way with mining. I can't force them if they've been paid to take through transaction fees 100 transactions. I can't say, but you must take 101. They can just go, bugger it, I don't want to work harder.
So you make the case then that miners actually have the absolute right to choose what they mine, what they choose to mine, and what work they choose.
Under the caveat that if they drop a block that other miners are going to accept, either they lose those fees, or if they do something a bit wacky in constantly rejecting all non-Catholic transactions, then all the other miners will reject them, and they'll continuously orphan blocks, and that miner will end up losing a lot of sort of income and probably go bankrupt.
One scenario that's been put to me before that I'm not sure that I have the best answer for is if a miner mines a particularly large block, doesn't another miner have an incentive to ignore that large block because there's a whole lot of transaction fees in that block that they could try and mine a competing block and get it?
Yeah, but they're going to be doing it after the first miner. So, I mean, think about it. If you have 30% of the network and the other guy has 40% of the network, and you discover a block first, you could say, well, he's got 40%. But the problem there is you actually have 60%, because if you get it distributed to everyone, it's going to end up, you have that block and other people accept it.
So what is it about the Bitcoin model that would stop a tragedy of the commons situation where a miner has 30% of the hash rate, mines a block, the other 70% all decide simultaneously, I'd be better off rejecting that block because I want to try and get the transactions? How would that sort of scenario play out? And is it even realistic for...
No, it's not really realistic. I mean, all it would do is fragment, and they'd have lots of little blockchains and no one would earn any money. Now, the difficulty is that you're assuming that they can take their money straight away. But the 100 block maturity level means that you have to actually get other miners to build on top of yours. So remember, you can't spend until it's 100 deep. So if you're going out there and kicking all the other miners off, then how are you going to do that?
Yeah. So if you got 20 evenly distributed miners and they all decide to start just mining their own blockchains because they don't want to let anyone else have any transaction fees, eventually some pair of miners are going to start mining each other's blocks, get longer, and the SPV clients will just ignore the other 18.
Exactly. Yep. So even if you've only got 3 miners at 30% and 1 at 10, and that 10 just hooks onto one of the 3 miners, then eventually they get longer and the other 2 30%ers lose out. So, I mean, what are they going to do? They're going to form a consensus together, and et cetera, and it all comes back to a big consensus.
So at the end of the day, the model actually makes, I guess it's one thing I've been fond of saying about Bitcoin is that the Bitcoin makes the default behavior the easiest path, or rather the path of least resistance is the one that is the best for the network as a whole.
Yes, correct. You just set up the economic rules, you make it most effective to play the game and not to cheat, and go from there.
Yeah. Back to governance for a moment. This is a question from me as part of the Bitcoin SV infrastructure team, and probably from some of the other people that have to make decisions about what we do. And in fact, it's a thing that has come up recently. Who should node developers be taking requests from, specifically with regards to the policies or the default policies that are implemented in the nodes? Because we are aware that setting of defaults actually does have some degree of influence, and it's an influence that we made some efforts to remove from ourselves after the Genesis. In fact, we quite explicitly said that in a message to the miners after Genesis activated.
Well, it would be good to set it so that the miners have, the nodes have their own control and they can work this out together. You don't want to see the miners colluding. I mean, that's the natural state of every business, of course. Old Adam Smith said that anytime you get two business people in a room, they'll start colluding about how to undercut the third guy. But at the end of the day, what we want to be able to do is allow the miners to have sort of open competition, but equally sort of not any special underhandedy things to cut this guy out. I mean, everything has to, that's why it needs to be open. So as long as everything remains completely open and without issues, then not a problem.
Okay, so I think almost all, there might be one or two exceptions, almost all of these configurable options, I guess, policies are configurable by miners at this point, and the one or two that aren't, we are actually working on making configurable. But the question is really, we have to at some point choose default settings for these sorts of things. We did go to the extreme when it comes to the consensus rules. There are only two left in Bitcoin, which is the maximum block size. Sorry, I might be mistaken, might be more than that. But there are two kind of critical ones. And we went to the extreme length of actually refusing to set a default, which means that you can't start a Bitcoin node without choosing those settings yourselves. That was quite extreme, but it's not really practical with policy settings because there's quite a lot of them. That would make it an incredible burden. So in changing default settings, like how should we as a dev team go about doing that? Our approach has been to informally gather a consensus of miners by listening to what miners are saying.
This is where the Bitcoin Association needs to grow into a proper commercial organization. I've mentioned, I mean, I've been a member for ever and a day of the IEEE, right back from when I did engineering in ancient history for half of the people listening to this who probably weren't even born. But the IEEE model is actually one that I find, either that or the ACM. The IEEE has a lot of good sort of professional processes, and that's one of the things we need to do. We need to start having business interaction, mining interaction, as this grows and commercializes, the same way that the internet, you have the internet sort of meetups between DNS people, between the standards bodies, between the major companies. People put in RFCs, which aren't standards, but they're treated that way. So all that needs to develop, which should be a function over time of the Bitcoin Association. Which I try and prod, but I don't want to kick into shape and get there. So I want to hopefully have it develop. I mean, I don't think half the people who read it even realize, but the Bitcoin paper is actually on a early IEEE publishing template. So.
That's why some of those look familiar then. I think it's actually almost the first conversation I ever had with you was the first time you raised IEEE, and of course I'm familiar with it because my brief stint at university was in engineering. And you'll be pleased to know that one of the aspirational targets for the Technical Standards Committee is to model itself on organizations like IEEE. So we're getting partway there. But yeah, okay. So that is it's a business layer function essentially, determining
That's correct.
what the backlog should be for the development team. Okay. Well, that helps us with some direction on how we should go about doing things a bit more in the future. So I want to jump back to the topic of SPV because I know it's dear to your heart, and it's something underdone in the past, and we've been doing a lot of work across the whole ecosystem, and others, many people have been doing a lot of work in trying to realize the SPV model in its reality. But I want to look.
I mean, just to interrupt, I mean, I think part of the problem was it became too easy just to leave the software alone and not build out, which I should have really taken a more active role in the past in this one. I mean, we've got to have our own, the whole block to validate. I mean, I keep forgetting not everyone has studied cryptography or hashing at a detailed level, and explaining to someone that the secure hash, the SHA-256 hash of the block is just as secure as the entire block, to a lot of people is counterintuitive. So, I mean, trying to say that this little 80-byte thing is equal to this 2 terabyte thing, people, no, but it is.
We've got to. Well, I think we've got to get better, and that's a broad cross section of people that the comment is targeted at. We've got to get better at explaining that because it is one of the most fundamental of Bitcoin.
Yeah, I mean, the thing, people go and, but there can be collisions in SHA, and what if it's broken, and what if, and you get all these counterfactuals. And the whole point is, if SHA is broken, then Bitcoin's broken. So, I mean, that's it. You've answered your own question. If the sort of SPV header is not secure, Bitcoin's not secure. Full stop. It's very binary here. There's no, oh, you lose a little bit of security. You don't. It's either 100% functional or 100% broken. It's very ASPI. It's like me, it's binary. There's no middle ground, it's black and white. Gray is just lots of little tiny pixels of black and white mashed together, and you have to look closely.
Yeah, okay. If you zoom in enough, you'll always get your binary response.
Exactly, because then you can hit the photons.
Aren't you lucky the foundation of the universe is quantum in nature?
Exactly. Keep telling people this one. But...
So Mike Hearn was probably one of the first people that ever really got SPV to any sort of degree, and for a really long time he was probably the only one.
Yeah, and I think that's probably some of his frustrations too, because he went out there and actually started building all of this, and then everyone says you're doing it wrong. I mean, yeah.
But it's literally been with us almost since the beginning, because Bitcoin J, which we still use in Enchain today, we've written some large chunks of it. Was first
I know.
Approximated an implementation of Bitcoin, SPV Bitcoin.
I mean, this is partly the irony in that people making my work into a religion have taken, but Satoshi didn't do this. Well, I mentioned in the white paper that it's meant to be there, and I do say I haven't got round to coding it yet. That doesn't, so if I said this is how you're meant to do it, but I haven't coded it yet, you don't need to wait for me to do every bloody thing on earth. And because, and yeah, I mean,
Well, why did you need to? If Mike went and did a lot of
Exactly. That was the whole point. I didn't want to do everything.
Yeah.
I mean, I had all these other things I needed to do, and I still do. So sitting there answering every question doesn't really.
I miss Mike. I think it was one of the towering figures of Bitcoin's early history, and he certainly did a lot of the hard yards in working out how to convert all of the Indian nightmares and on the Java side, without which I would probably have lost a lot more hair.
Yes, I will do the sort of whack myself with the ruler for that one. I know that's always been a big problem, which is the typical. I mean, ironically, I quote Mythical Man Month effectively in the original source code, and yet I don't put all the requirements of what I've actually quoted. So, I mean, that's my own hypocrisy there in saying that you need to do X, Y, Z and referencing that I know this and then not doing it.
Well, you might be surprised to know that I've recently made my peace with Little Endian, and I've actually come to prefer it for certain applications, even inside Java, which is natively Big Endian by default. So that's a long and extremely nerdy conversation to explain why I feel that.
Well, I mean, I think part of that comes down to the platforms. I mean, Sun always chose one particular Endian state, and of course Java originated from Sun. Then Oracle, of course, merged with Sun. And I think some of that happened just because they wanted to be the opposite of Windows at one stage. But I mean, I'd actually say that, but the reality is I can't, because Windows actually goes back even further. And for those who remember, Windows, in its current form anyway, the NT4 ORN, was birthed out of VMS. And I have a background in VMS. So I got torn in the middle because I worked on both Solaris machines and VMS machines, which were DEC, and DEC ended up becoming sort of the foundation for what we have as Windows. The only problem was I don't know how the hell Microsoft took a working bloody proper operating system in VMS and made it into Windows. But I think they got every good bit of VMS and hit it with a hammer.
Yeah. You're talking about the deep dark past. I remember VMS, and of course, if we're talking about that, there's a topical Vax joke that we could be making right now, but I'm not going to steer right.
Yep.
Right. Well, I mean, you've opened the door, so basically, it's because of Terranode, the fact that we want it to be able to run on commodity hardware, the vast majority, which is Little Endian by default, and we need to do a lot of mirroring data. And it turns out that even Java does that pretty damn fast with native instructions if your data is Little Endian to start with. So that's the secret behind my nerdy revelation. So getting back to SPB, it is the model that is intended for the vast majority of users of the Bitcoin network who interact with the network. Skipping forward to 8 billion, and by that time it may be more than 8 billion people, which might actually imply a lot more than 8 billion devices, will need a copy of this 80-byte block header that arrives on average once every 10 minutes. How do you think we're going to go about distributing those? Because distributing to 100,000 users 80 bytes is a different ball game to sending it to everyone on Earth.
I mean, you've mentioned a number of peer-to-peer protocols, and there are some good ones out there. So eventually, I think we're going to have to look at something like that. It needs to be some sort of peer broadcast media. Structured overlays will also be probably part of it too, because we want people to not have to search. and to find all of this quickly, potentially just even subscribe to a push model where it goes everywhere. It's really unfortunate that unicast is not publicly available. That would be super cool and all the rest. But I mean, there are ways around that. There are ways to actually get unicast over public networks, but it just means a hell of a lot of coding and doing everything ourselves because no one makes tools to make it easy anymore.
So fundamentally, I mean, broadcast is the model. So what about radio? Could we use mobile towers to broadcast block headers?
Yeah. I mean, this is the only sensible way of, like we mentioned, Blockstream. The only sensible thing they could have done would have been having their Blockstream satellites do this, except that's really an expensive, stupid way of doing it the way that they have. If you had LEOs, low Earth satellites, and giving it internet, yes, but you're better off hijacking a little bit of background bandwidth over 5G or making an agreement with mobile carriers. In the future, if this gets big enough, then it just becomes like background to the internet.
Okay.
So,
and you can cross that, check that in the background with service. You just periodically check the latest blockade.
For instance, if BT over here sort of had connectivity that was paid for that way, then equally they'd probably want to have a update service. And all you'd do is update whatever you had from the last time you were connected to 5G. And so it might be a 2 meg download. And 2 meg downloads over 5G. I mean, that's assuming you've been overseas and off their network for a couple of weeks. And not like everyone these days who then pays for a foreign SIM card and downloads it anyway.
So I wonder if anybody watching this caught the reference to the Blockstream satellite and is interested in approaching Blockstream and asking if they could change space blocks to space headers. Okay, I'll behave now. What about BitTorrent as a mechanism?
BitTorrent's not too bad. It's not the most efficient protocol. Funny enough, mentioning some of the other people, I've mentioned many times Mnet and the related protocols to that. That was actually our old friend Mr. Zuku there. He was involved with that before it fell apart. So, I mean, it's interesting that he runs around now saying how proof of work, Bitcoin's the first proof of work system when he was working on a proof of work system a decade before Bitcoin.
And he just didn't know?
He must have known.
He didn't realize.
I mean, it didn't have the economics though. They reset, I mean, they had this sort of socialistic idea that if anyone gets too much money, they'll just reset the network.
Yeah.
Which makes it valuable. I mean, no one's going to get too powerful because if they have too much money, we'll just reset it all and start again.
That happened once in Bitcoin.
That encourages people to invest. If I get too much money, they're going to reset my money, so I better put lots into this network.
So it actually has happened in Bitcoin history with the testnet because people started trading testnet coins and got worried, so they reset.
Oh no, I heard about that.
Testnet 2 and testnet 3 now, and the old testnet 1 is dead. Yeah.
I mean, this is the altcoin world. Oh, testnet coin, yeah.
Well, I'm glad you mentioned proof of work because it segues nicely into the last area that I want to cover with you, which is the topic of energy usage and energy waste. This is something that gets talked about a lot in media about Bitcoin in general, but
you know, the Earth wastes a huge amount of energy. 99.8% of the solar energy that just comes and hits this planet gets just flung out into space unused. It's horrible that this planet could sit there and waste all this power that could be used for productive means.
including running Bitcoin.
Including running Bitcoin.
So I want to ask a question which might on the surface sound like I'm challenging a notion that that has been put about before. I've heard you speak about how it's critical to Bitcoin that the energy used in proof of work is used only for the proof of work, and that it is essentially wasted on that and that alone.
Yes.
That word waste, I guess I want to go into, because the expenditure of energy used to produce a valid block header through the proof of work process, it adds some weight to the trust proposition of that bit of data, doesn't it? Before that, it's useless data, but now someone spent a lot of money that they're going to use if it turns out that data is false.
So I've said many times that it's the peacock tail, and we could say that the peacock tail is very wasteful, but it also has value in that the peahen goes to the guy with the biggest tail. So to the peacock, you could argue that it's not wasting, even though it's wasting.
So could you also argue then that there is some value to the peahen in being able to choose the fittest of mates out of a selection, but being able to figure out which one is actually the one that's worth, I guess, trusting your future?
Exactly. So what it does is, I mean, it de-anonymizes nodes. This is, of course, what some of my opponents really don't like. The whole purpose of proof of work is to make sure that nodes can never be anonymized. You can't run them on Tor. You can't hide them. As a user, you can do all sorts of things, but as a node, you can never be secret, which means you're always under the requirement of law. There's no anonymity. There's no screw you, we can do whatever we want. I mean, the reality here is nodes are always a controllable entity. So very simple. You can always take legal action against them. You can always sue them. You can always have government come and raid their building because they're acting as a botnet. So that's what it comes down to.
And this goes to the property of Bitcoin that acting honestly will always produce a strictly better result for you than attempting to act dishonestly, because part of the downside of the dishonest act is you will get caught.
Correct.
You'll be known by everybody immediately and you're too big to hide.
Correct.
So is there any truth to the idea that a block header, before you've established that it has proof of work, is a piece of data that anybody could basically forge? After the proof of work is done and this peacock's tail, I suppose, property has been added to it, that data is actually a lot more valuable to people because they've got some basis on which to trust that the data is actually true.
They now know that there has been an effort made in validating, and there's something at risk.
So is it true to say then that the energy that is expended on mining that block hash solution, in some way, the energy transfers value into the data, and that you're actually transforming the energy itself into value in some sense?
I don't know if you'd say you're transforming it into value. I mean, it's part of a work process. So putting on my engineering hat once again, work is transformed energy. So you take power, the electricity, and you transform power into work, and work has a productive use by definition. If you're just running around idly for no reason, then it's not work. If you're doing it to exercise, you're doing it to win a race, then it's work. So at the end of the day, it is a proof of something that is creating value.
It has this interesting property in crossing geographical boundaries that energy might otherwise not be able to cross so easily or efficiently, though, doesn't it? I mean,
it does. So one of the things we've discussed is sort of where you put energy devices. And with the ability to very simply send a small update packet that just has part of the header, you can distribute the hash solving and the ordering of blocks separately. And for instance, if I have a facility, and this could be distributed even more, I could put right on the internet sort of hub point where I collect all my blocks together and send them out to other miners. One of the main sort of routers, like in California, for instance. But then I could have a simple ISDN link that's intermittent back to somewhere in the middle of the Sahara Desert. And that facility could be using solar energy to run these machines that find the hash puzzle. And then very quickly and effectively, they just send, this is the winning hash, and what you need to put it together. And then the remote unit constructs it all together, sends it out, and earns their money.
And this essentially allows us to make use of energy that would otherwise be inaccessible to us, because transmitting 1,000 miles or 10,000 miles over high voltage power lines incurs so much efficiency loss. Where you can actually just use it at source.
Yeah.
So I was going to ask you before, when we were talking about the different actors, actually, what the right term is for the people who do the hashing, but I suspect after that conversation, the answer is contractors.
Could be part of your own company. I mean, a branch. I mean, it could be a partnership. It could be all sorts of things. But yes, it's a subcontractor, most likely.
Yeah. Okay, well, that brings me to the end of our questions, and I think that we're probably running over our time slot, as is normal for these sorts of things. So thank you very much for joining us again, Craig.
Yep.
And this brings us to the end of day one of our DevCon. We've got more things tomorrow. I'd like to close with one last question, which I guess is more for the app developers. And many of the people who'll be watching this today. The work will never be finished in terms of building the Bitcoin SV ecosystem, the infrastructure, the companies around it. But
you don't want it to finish.
Well, no, we get bored, wouldn't we? And then,
exactly.
Yeah, and then we'd have to retire or I don't know, go fishing or take up some other silly hobby. Yeah. So I don't think I'm ever going to ask you the question, are you happy with the state of Bitcoin? Because I don't think the answer will ever be yes. There's always going to be more to do.
Always be a caveat, yeah.
What are you happiest about in terms of progress over the last
Oh, that we are actually making progress, to tell you the truth. That we're developing, that we're growing, that people are starting to use Bitcoin, make apps for Bitcoin, experiment. That people aren't sitting there asking me what I'm doing and saying, how do I do it? But rather actually trying to learn themselves.
Yeah. And I think that is testified to by the fact that we actually have people here at this DevCon trying to learn more about how they can interact with Bitcoin, make use of the core infrastructure and the tools. So, all right, we will draw a line there. So thank you very much again.
You're welcome.
Dr. Craig Wright, and we will see you at another event very soon, no doubt.
No problem. Okay.
Well, it's always interesting to dig into the depths of Craig's mind and get some insights into some of the early decisions of Bitcoin. And that brings us to wrapping up day one of this DevCon. I hope some of you managed to pick up some airdrops in the breaks in between presentations. And we've got a whole lot more for you tomorrow, including a dive into nano services, a new type of dust return transactions, a lot of commentary on long chains and ancestor limits. We'll be joined by Hancash to show the Connect API, Xiaowei to show us some of the esoteric uses of push TX. Hayden from the Electrum SV team will be showing us their SDK, and of course David Case from Chronoverse will be showing us the Fix SDK. On top of that, I can tell you that there is also going to be a surprise. So please join us again tomorrow for some or all of the presentations. I'll look forward to it, and I will see you then.
you.